It's a great pleasure to have yet another LXMLS. The hosts are, as usual, the University of Lisbon through Instituto Superior Técnico and Instituto de Comunicações. And we are co-organizing this school with UNESCO ID and Babel, Pribaram, and Cleverly. And this is only made possible thanks to our sponsors. So I'm including all sponsors here. Our gold sponsor is Google, our bronze sponsor is Cleverly, and we have several partners, including Técnico, UNESCO ID, Instituto de Comunicações and Babel, Carnegie Mellon Portugal, the Alice Network, and Pribaram. So one thing that should be emphasized is that at IST in Lisbon, we have many people working in machine learning. We are part of the Alice network through the Alice unit called Bloomless. And if you are interested in a master program or a PhD program at IST, there's many opportunities related to machine learning, natural language processing, data science, and other topics. So these are the organizers of the summer school. Most of them are here, except those whose time zone is not very friendly. So every time you see our names, or either here in Zoom or in Slack, we usually have an organizer prefix associated to our name. So if you have any questions, reach out. So there's also a steering committee that has been involved since the first edition of the summer school, including myself, Fernando Pereira from Google, Isabel Troncoso from IST, João Graça from Unbabel, Luís Charmento from Google, and Mário Figueiredo from IST. And another thing that is crucial for making the school work is our monitors. So we are fortunate to have the help of a lot of monitors to help with the lab sessions, to help with the logistics of the school. So a big thanks to all of them. And just a few quick information. So this year, unfortunately, the school is going to be remote, like last year, and like the 9 first editions, and hopefully unlike next year. So we are going to be communicating primarily through Slack. So you should have received an invitation to Slack. If you haven't joined yet, please do so. And if you haven't received the email, let us know as soon as possible. This is where we are going to centralize the communication about the school. Where we're going to have Q&A related to some of the talks, and also how we are going to make announcements to students. Then there's the Zoom where we are right now, and where lectures will be held and Q&A will take place. The lectures will be streamed in YouTube, so you can access this link for watching the lectures online. They will also stay there after the school is over. And finally, we have GatherTown as a space for socializing, among students, organizers, and speakers. You should have received all this information in the email that Fernando sent yesterday. And just to recap today's schedule, so I was just informed that there was a mismatch with the announcement that we had in Eventbrite. So all these times are in Lisbon time. So the first lecture is going to start right now by Mário Figueiredo. It's a probability theory refresher. Then there's going to be a small break, and then a second lecture, which will be an introduction to Python by Luís Pedro Coelho. Then in the afternoon, there's going to be a lab session. And at 5, we are going to have a virtual welcome reception in GatherTown. All right, so this is the plan for today, and enjoy the rest of the week. Enjoy LXMLS 2021, and I hope to see you, some of you next year presentially. For this year, this will be remote. Thank you very much, and I will pass the mic to Mário Figueiredo. Mário Figueiredo is a full professor at IST, distinguished professor. And he has a lot of work in machine learning and statistics, sparse modeling, and many other topics. Is one of the organizers of the summer school, and is going to teach his usual lecture, an introduction to linear algebra, probability and statistics, a refresher. So Mario, the floor is yours. When you are ready, you can start.
Thank you, Andre. So you need to stop sharing your screen.
Yeah.
Let me see if this is working. Okay. Can you see my slides? Yes, I guess so.
Yes.
Okay. So good morning. Thank you, Andre, for the introduction, and welcome everybody to yet another, the 11th edition of LXMLS. Unfortunately, like Andre mentioned, it is online. It's not live. It's so much better when it's live. So what I'll do today, so the goal of today is, so I've been teaching these introductory, say, math tools lecture for the past 10 years. It's been evolving slowly, but it's probably the part of the school that has least changed in these 11 years, because it's things that don't change very fast. So the goal, of course, is not for you to learn about these topics from this lecture, but I see it as a warm-up. I'll try to warm up your brains, because a lot of you will know a lot of these. Then the hope there is that you feel good, because you think, okay, I know this is good, I know this, I know this, I know that. If you don't know a lot of these topics, if you don't know most of these, you should be worried, because most of these are tools that are needed to work in machine learning, at least in advanced machine learning. And so this is sort of similar to what I teach in my machine learning course in the first couple of weeks, but it's a condensed version and selection of topics. So I hope you gain something from it. At least I'll try to start your brains so that now you get ready for the rest of the school. Okay, so why do we need mathematics for machine learning? Maybe you don't need convincing, you all know these, because machine learning is a highly mathematical area. It involves, so this is kind of an arbitrary depiction of what percentage of different areas of mathematics are involved in machine learning. So of course, we need a lot of linear algebra, we need probability theory and statistics, we need calculus, we need to know about algorithms and others. So I will not cover all of these, of course, it would be impossible. I'll cover essentially basic tools of probability theory, basic concepts, not tools. And then I'll talk a little bit about some basic stuff in algebra, which is central in machine learning. So what is probability theory? So probability theory, in a sense, is a mathematical theory that describes probabilistic models. We have to this word is very loaded. What does probabilistic mean? We'll get into that in a second. But probability theory describes how data, how things that we observe in the world, which are random or probabilistic in nature, how we can describe what we know about these mechanisms of where data and observations that are random in some way are produced. And the reverse arrow that you see in the drawing, going from data to models, is called inference or learning. And so this makes it clear that probability theory and probabilities play a central role in machine learning, because the goal in machine learning, of course, is to go from data to models in a very general, very wide sense. So probability theory historically had its roots in games of chance. People tried to come up with clever ways to win playing dice or cards or whatever. And that's where essentially probability theory was born. But then it became clear that it has a central role in science and in the understanding of the world. And so most of the great names of science were involved and contributed very strongly to probability theory. And there are lots of missing names. Even you could put there Einstein and Heisenberg and Schrödinger. All of we just need to think about quantum physics nowadays to understand how important probabilities are. And probability theory is the correct tool. Is actually can be shown that it's the correct tool to handle uncertainty, information, knowledge, observations, and so. Also, of course, the inverse process of learning, decision-making, inference, all of which is all of science, essentially. So the question you could ask is it still important to know, have a solid background in probability theory in this modern age of deep learning, where you can just hook up some PyTorch blocks and get things to work? Well, I would argue yes, and this is not the first time I show this. I tried convince you if that would be necessary by showing this index, this table of contents of the first chapter 3 of a recent book, which is all about probability theory and information theory. So we'll cover most of these topics during this talk, during this lecture. And I would challenge you, what book is this from? Okay, probably some of you know, but I don't know if you do or not. So this is chapter 3 of the deep learning book, the famous deep learning book by Ian Goodfellow, Joshua Benchu, and Aaron Kurville. And this fact alone is enough to convince people that, okay, although we have deep learning is a complicated topic, with a lot of mathematics, with a lot of probability theory and algebra and all of these tools. So it's not enough to know the programming tools, the frameworks, the toolboxes. If we want to have a lucid view of what's happening, we need to know the mathematical underpinnings of these areas. Okay, so let's get started with the actual topic. So what is probability? This is a tricky question. What do we mean when we say that the probability of a randomly drawn card, being a clubs card, is 13/52? Or what do we mean when we say that the probability of getting a 1 when you throw a fair die is 1/6? Well, there are different definitions. So there's the classical definition by Laplace in the early 19th century, which says that if I have n mutually exclusive equally likely outcomes, and A of which result in the occurrence of A, then this number NA divided by n is what we call the probability of A. For example, this in the first example, if I randomly draw a card, I have 13. So NA would be 13 number of outcomes, possible outcomes that will give me a card of clubs. So of course they are mutually exclusive because there are 13 different cards, and the total number of cards is 52. So this is how we intuitively compute probabilities. We use the Laplace definition. There's also the frequentist definition, which says, okay, the probability should be defined as you do this experiment many times, many times. You draw a card, you count how many times you got clubs, say. You divide by the total of draws you did, and in the limit, if you do this experiment infinitely often, then this limit should be what we call the probability of A. And there is also the one which is very important for inference, which is the subjective interpretation, which says probability of A, probability of something, is a degree of belief. It's how much I'm willing to bet on that thing happening. And this is very important because it gives meaning to statements such as the probability that it will rain today is 0.2, or the probability that after observing some exams, you say probability that patient A has some disease is 0.72. So of course, none of the above definitions will work here, because there's only one today. So the probability of raining today is an expression of a belief in something that will happen or not an expression of a relative frequency of something occurring, because there is only one today. There are not infinite todays or as many todays as I want to try again and again. Okay, these concepts are actually philosophically delicate, and the concept of probability is not as simple as you think. You can read about it. I'm not going to talk about it. So there are all these different. There's yet another one which I didn't talk about. But the important thing for us is that the mathematics of probability can be developed and built and formalized in a completely axiomatic way without having to worry about interpretations. So regardless of what we think probabilities are, and this is an open discussion topic among philosophers of science, we can just go on. Okay, what the key concepts, and these were essentially developed by Kolmogorov in the early part of the 20th century, are the following. So we have a sample space, which is a set of all possible outcomes of some random experiment. So for example, if you toss two coins, your sample space is heads, heads, tails, heads, heads, tails, or tails, tails, which are the possible outcomes. Or if you play the roulette, every time you play, the possible outcomes are the numbers 1 to 36, and so on. I could go on and on with more and more examples. And we call event to a subset of the sample space. So for example, an event could be a specific outcome, one element of the sample space is an event, but a subset, say, in this example, the first example, getting exactly one head in a two-coin toss. So this would be tails heads or head tails, which is a subset of the whole sample space. So in the case of when the thing that you observe is not just a discrete event like getting a certain card or a certain number of cards or something like that, but something like a real number, like say you toss a die and you're not interested in the face, but you're interested in how far did it go, or where will the next raindrop fall on a given square tile somewhere, okay, which will be some position in R2, some pair of numbers. To handle these cases, we need more sophisticated mathematics, sigma algebras, Borel sets, measurable functions, so on and so forth. Of course, this is mathematically heavier stuff, which is important in some areas of machine learning, but not so important, and we will not look at them. Just I wanted to mention them because they exist and they're important. Okay, so Kolmogorov came up with these axioms in 1933 for what the probability should satisfy. So probability is a function that maps events. What do we mean by mapping events? Given some event, I'm able to compute its probability. And the probability is a number between 0 and 1. So it maps events into the interval 0 to 1. And it needs to satisfy these axioms. Any event has a non-zero, as a non-negative probability. The probabilities are never negative. They are larger or equal than 0. It could be 0, it could be larger than 0. The probability of the whole sample space is 1. Okay, it means essentially it captures the idea that if you do the experiment, something will happen. Okay, so if you consider the whole sample space as the event, something happening, then something will happen, and so the probability of something happening is 1. And then this is the more technical axiom, which says if you have a collection of events that are disjoint, then the probability of their union is the sum of their probabilities. And of course, you use these every day when you intuitively say, what is the probability that when you throw a die, you get an even number, say 2, 4, or 6. So you can think of 2, 4, or 6 as three separate events, so subsets with a single element. They're of course disjoint because 2 is just a set with one element, 4 is another set with one element, and so on. And so the probability of getting either 2, 4, or 6 is the sum of the probabilities. So this is kind of intuitive and easy to accept, and that's how we reason intuitively about probabilities. And from these axioms, we can derive many results that we could spend the whole morning deriving events about deriving probability facts. So I will not do any derivations. I will just give some examples. We can easily show that, for example, the probability of the empty set needs to be 0 because the empty set is disjoint from any other set, and because the probability of the whole space is 1, the probability of the empty set needs to be 0. But for example, if a set is contained in another set, meaning if an event is a subset of another event, then its probability needs to be less or equal than the probability of the event that contains it. Or that the probability of the union of two sets is the probability of the sum of the probabilities minus the probability of the intersection. And this is easy to understand intuitively because essentially when you add the probability of B with the probability of A, you're adding the intersection twice, and then you need to subtract it once to get the probability of the union of the two sets. And because probabilities are larger or equal than 0, and for whatever you put inside P, if you take this out, you get something which is larger or equal. Of course, this is less or equal than these, because this becomes larger or equal than above. And this is very well-known inequality, which is widely used in machine learning, at least in theoretical machine learning, which is called the union bound. That the probability of the union of two sets is less or equal than the sum of the probabilities of the sets. Okay, what about conditional probabilities and independence? If we have a set which has non-zero probability, and this is only possible if this set B has non-zero probability, then we say that the probability of A given B, or probability of A conditioned on B, or the condition probability of A given B, so there are many ways of saying it, is simply the probability of the intersection divided by the probability of this set B. And this has a very simple meaning. What I'm asking is, what is the probability of the intersection? What is the probability of A happening, given that I'm inside B? So if I'm inside B, this is it's like B becomes the new sample space because I'm telling you I'm inside B. And given that I'm inside B, what is the probability that I'm also inside A? So it's just the ratio between the intersection. What is the fraction that the intersection represents in the probability in B? So it's probability of the intersection divided by the probability of B. And that's that's how it's defined. It's just a definition, but it's an intuitively acceptable definition. And it's easy to see that this conditional probability satisfies all of Kolmogorov's axioms. So of course, probability of the whole sample space conditioned on B is 1, because of course the intersection with the whole of B with the whole sample space is just B itself, and so on and so forth. And it's easy. I'm not going to go into the. I'm not going to bore you with more details. It's kind of easy to see that they're all satisfied. Finally, this very important notion, which we use every day when we deal with probabilities, which is independence. We say that two events A and B are independent, and we write them as B, this inverted, looks like an inverted pi, B. We say that two sets are independent, two events are independent, if the probability of the union equals the product of their probabilities. Okay, this is a definition. This is not a very intuitive definition in terms of geometry of the space. We need to come up with some. So there are lots of illustrations of these with drawings, but I find them all a bit misleading. So I'm not showing any visual illustration of what independence means between sets. But I think actually a more intuitive view of what independence is for sets is it's in the relationship with conditional probabilities. Okay, so if P of A and B, if P of A and B in the numerator is the product of P of A times P of B, then the conditional probability of A given B, when you put this product up there, you cancel out P of B, you get just P of A. Now this is an intuitive statement of what independence means, because it just says that the probability of A given B equals the probability of A. So it means that knowing B or not knowing B doesn't make any difference, which means that A is independent from B. So you don't care whether you're in B or not, the probability of A is the same, which means that A does not affect this probability, B does not affect this probability, and so these two events are independent. So let me give you a very quick example for those of you who don't remember this so clearly. So suppose you have 52 cards, that's your sample space. Say set A is the fours, the four of the four suits that we have. So hearts, clubs, diamonds, and oh, this is repeated. It should be spades. I'm sorry, this is wrong. One of these symbols is wrong. And set B, say, is the cards of hearts. So the probability of A is 1 over 13, because the probability of getting a 4 is 1 over 13, because it's 4 divided by 52. Probability of getting a B, which is getting a hearts card, is 1 over 4. Okay, so the probability of the intersection, what is the intersection between the set of fours and the set of hearts, is the 4 of hearts. And so the probability of a single card is, of course, 1 over 52. Okay, but the probability of A, which we know is 1/4, and the probability of B, which we know is 1 over 13, when I multiply them together, I also get 1 over 52. And so this shows that these two, getting a 4 or getting a card of hearts, so the figure in the card or the suit are independent. Another way of expressing this is that getting a 4 given a B, so getting a 4 given that you know it's a card of hearts, it's 1 over 13, which is just the probability of getting A, which is getting a 4. So knowing when you know that the suit of the card, you know more about what type of card it is than if you didn't know what suit it is. So if you play card, you know this very well. Okay, Bayes' theorem, okay, which is a central tool in modern machine learning, very central tool. So for in this case, for dealing about talking about sets and events, the way it's usually presented and introduced is in this way. So we have something called the law of total probability, which states the following. Suppose you have the sample space is X and you have a partition. What is a partition? So a partition is a collection of subsets that are disjoint. Okay, so these A's are disjoint. When I intersect A2 with A3 or A3 with A4, I get the empty set. And their union, the union from A1, 2, 3, 4, 5, makes up the whole X. Okay, in this case, I can write P of B. I can write the probability of B as the sum of the probabilities of the intersections with B with each of the AIs. It's easy to see, right? The probability of B is these plus this part plus this part plus this part plus this part. And so this is called the law of total probability, which we'll come back to in a second. So by theorem, what it says is that if we have this partition, that the probability of being in one of the sets of this partition, given that you are in B, okay? So we just have to invoke the definition of conditional probability. So this is just the probability of B intersection with AI. This is what we had in the definition of conditional probability, is the probability of these, one of these intersections, divided by the probability of B, which is obvious that it is, right? Because the probability of being in, say, in A2, even that you are in B, is the probability of this region here divided by the probability of B. But now we invoke the law of total probability to rewrite P of B in this way. And this is one of the different ways in which Bayes' theorem appears. It's also called, and it's interesting to keep in mind, that this is also called the law of inverse probability, because it allows us to, from knowledge of the probability of B given A, infer the probability of A given B for each A. So it inverts the order of this conditioning using this expression. But for that, we need to know the probability of the A's. And the denominator, if you examine it carefully, you'll notice that what it does is simply normalize things that guarantee that when if you sum these across the AIs, you get 1, because that you need to get the probability of the sample space, which is, of course, 1. Okay, actually, Bayes' theorem and some simple form of Bayes' theorem of Bayesian inference, I argue it should be known by everybody. By everybody, should be taught in high school, because there's lots of misinformation and misleading reasoning going around, because people don't really understand these very fundamental notions of how can we infer the probability of something from observations. And let me start with this. Well, I have a picture of Bayes and Laplace on the left. So Laplace is here because Laplace was actually the person who put Bayes' theorem in firm grounds. So it is a very active, a very timely thing to talk about tests and diseases and sickness because of COVID. So this is a classical issue in probabilities. What is the probability that you are sick, given that you tested positive for something? Okay, and I illustrate this with this picture. So suppose you have this big population, this blue population. The sick people are these little red rectangle, and the test is here. So this is a test. This is the fraction of the population that tests positive. So this is a test with a reasonably high positive, false positive rate. This is just for illustration, because this green here outside of the red are those people who test positive but are not sick. The intersection is the people who are sick and test positive. And the little red thing outside there is the people who are sick but do not test positive. So that is so-called false negatives. And so it's very easy to use what we saw in the previous slide, just to come up with what is the probability that you are sick given that you tested positive. So it's just the probability of testing positive and being sick, which is this intersection between the red and green areas, divided by the probability of the test giving positive, which is the fraction of the green rectangle divided by the whole population. There's an important number, which is the ratio between the red and the blue. So the population that is sick and the whole population. It's called the prevalence, which is the probability of having this sickness, this disease. And now, just using what we saw in the previous slide, we can write down this as probability of testing positive given that you are sick. This is called the sensitivity, or the true positive rate. How likely it is that if you are sick, your test is positive, times the prevalence. This is just what we saw. So the joint probability is the product of the conditional times the marginal. And then we simply use this law of total probability here. In this case, it's just for 2 cases. Probability of testing positive given that you are sick times the probability that you are sick, which is equal to the numerator. And the probability that you test positive given that you're not sick times the probability of not being sick. And this thing here is called the false positive rate. It's the probability that you are sick, that you test positive although you're not sick. And probability of not being sick is 1 minus the prevalence. It's the blue area except for the red divided by the total area. And so, for example, if your test has a high false positive rate, then this increases the denominator, decreases the probability that you are sick given that you tested positive. So these combinations of these numbers are very important. So when we talk, I think everybody should know this. This should be taught in high school. Lawyers, teachers, everybody should know about this. it's hard to reason in the modern world without knowing Bayesian inference, at least this slide. So there's this nice cartoon from XKCD where these two people are talking, and they have built this neutrino detector that measures if the sun has exploded. So the sun has gone nova. So the question is, did the sun just explode and we're all gonna die? So it detects if the sun has exploded, then it rolls 2 dice. And if they both come up 6, which has something which has probability 1/36, which is low, then it lies. It tells whatever the reverse of what it observed. Otherwise, it tells the truth. So they turn on the machine rolls the dice. It says, yes, the sun has exploded. And the statistician that says, okay, the probability of this result happening by chance is 1/36, because there's only one chance in 36 that it lied, because it needs to have 2 6s. And so, because 0.027 is a very small number, there's a very small probability of this happening by chance. The statistician concludes the sun has exploded. But the Bayesian statisticians, who knows the prevalence, he knows the probability of the sun exploding is very, 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 very small. He says, I bet you $50 it hasn't. So this combination between observations and prior knowledge is at the heart of Bayesian inference, and should be widely known. Okay, let's jump onto a little more technical stuff. So random variables. So what is a random variable? So a random variable is a function from some random event, some sample space, into, say, the real line if you have a real random variable. Or it could be R2 if you have a 2-dimensional random variable, and so on and so forth. So it's a mapping. So for example, and I'll have an example in a second down here. If this sample space is the one associated to tossing 2 coins, so my sample space is heads, heads, tails, heads, tails, heads, tails, and tails, tails, and I can define a function, x, so x is a function that takes the possible outcomes of the experiment and produces a number. In this case, I'm saying that this number is the number of heads. So the number of heads in heads, heads is 2. And in heads, tails, or tail heads is 1, and in tails, tails is 0. But it could be something else. You could define whatever function you want. It could be the square of the number of heads, or the logarithm of the number of heads, or the number of heads divided by something, or whatever. It's completely arbitrary. It's any function that you want to define on the outcomes of a sample of random experiment and gives you numbers is called a random variable. There's some technical conditions, but I will leave them aside. So the range, so the possible values that the function takes in this case is 0, 1, 2, because the number of heads when you toss 2 coins is either 0, 1, or 2. So we typically study separately discrete random variables and continuous random variables, although it's possible to study them together. But so when the range is countable, so for example, natural numbers or just 0, 1 or 0, 1, 2, where it's countable, you can count it, you can map it into the natural numbers. Then we say we have a discrete random variable. When the range isn't countable, say it's a real line or the interval 0 to something, or R2 or something, then you say we have a continuous random variable. For example, a continuous random variable would be the distance traveled by a tossed coin or something like that. Okay, so how do we get probabilities for the random variable? So we know how to get probabilities on this side. On this side, that's where we define probabilities. And so we define the probability on this side with the help of the probabilities on this side. So for example, the probability of some number, of some outcome, little x, which we call fx of x. So I'll use this notation as much as possible because this is the correct notation. I say the probability mass function of the random variable big X computed at little x is the probability of all the outcomes on this side such that they map their function is equal to x. So I would need to go into this side and check what are all the little omegas, all the values, all the outcomes on this side that map exactly into little x. And the probability of this set is precisely how I define the probability of x, or probability mass function. For example, if you toss 2 coins, you know that you have a probability 1/2 of getting 2 heads, because it's either head tails or tails heads, and a probability 1/4 of getting only 1 head, or 0 heads or 2 heads, because for 0 you need to have tail tail, and to have two heads, you need to have head. So there's only one outcome in the random experiment that gives you a 2, only one outcome that gives you a 0. They both have probability 1/4 because we have 4 possible outcomes, equally likely. And there are 2 outcomes that give you a 1 head. And since you have 2 outcomes, it's 1/2 probability because it's 1/4 plus 1/4. Okay, so there are lots of important discrete random variable. I will just briefly review what are probably the most important. So the uniform. So the uniform is when the probability mass function is equal to the number of possible outcomes. So the inverse of the number of possible outcomes. So for example, if you have a roulette, the probability of each number is 1/36 because distribution is uniform. This is what we call uniform distribution. Doesn't matter what little x is, the probability is always 1/36. Or if you throw a fair die, the probability was 1/6, and so on and so forth. Another very important random variable is the Bernoulli. This is one of the most important, of course, which is a binary random variable which takes value 0, 1, or any other pair of numbers, but 0, 1 is the conventional choice. And we have 2 probabilities. It takes probability p that it gives you 1, and probability 1 minus p that you write it that you get 0. And there's a compact way which is very useful, and you will use it throughout the school of writing these probabilities in a compact way, which is you take p and raise it to x, you take 1 minus p, raise it to 1 minus x, and this automatically gives you this, because when x equals 1, you get p raised to 1, and 1 minus p raised to 0. Whatever you have here raised to 0 will give you a 1, so you just get p, and vice versa. So this is a very common way to write compactly things that depend on binary variables. Example of a Bernoulli variable, a coin toss, where heads is a 0, tails is a 1, and if you have p equals 1/2, then you say you have a fair coin. If p is not 1/2, you say that you have an unfair coin, a biased coin. Binomial. The binomial is the sum of n Bernoulli random variables. So you toss a coin n times. What is the probability that you got x heads? Okay. And this is given by something called the binomial probability distribution. So the probability that you get n heads is the probability of heads raised to, that you get x heads is p, which is the probability of getting a head raised to the number of heads you got. 1 minus p raised to the number of tails you got, because if you get x heads, now you get n minus x tails, because the total is n. And I have this coefficient, called n choose x, called the binomial coefficients, which count in how many different ways out of n tosses you can get x heads. It's a combinatorial number that counts, because you can get, if you throw the coin 3 times, and you want to know what is the probability of getting, say, 2 heads, you can get 2 heads in different ways. You can get the first 2, or the first and the third, or the second and the third. So there are different, you need to count in how many different ways you can get 2 heads out of 3 tosses, or x heads out of n tosses. And you can, so the probabilities look like this. So suppose, for example, that you toss 40 times a coin, and the probability of getting a head is 0.5, so you have a fair coin. So this is the probability. So the more probable values are around 20, because if you have a fair coin, you expect that if you toss it 40 times, you expect to get around 20 heads and 20 tails, so not too far. So the higher probabilities are around 20, and then it tails off when you move away from this expected value of 20 in a certain way, which is given by this expression. So these plots are for this expression for different values of n and p as a function of x. So the horizontal x is x, like I just said. Okay, another very important distribution, discrete distribution, the discrete random variable, is the geometric, which is kind of related to the binomial, but notice that there is no x here. So what this means is that it counts, it measures the probability that you need x coin tosses until you get the first head. So it means you failed x minus 1 times, which has probability 1 minus p raised to x minus 1, and then finally you succeeded. So there's a 1. So this is the probability that you need 7 coin tosses to get the first head, which means that the first you get tail, 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 tail 6 times, and then finally head. And finally, for the discrete random variables, we have the Poisson random variable, which is ubiquitous in many areas of science, and not only science, but in life, which is ubiquitous because it models everything under a very, very general assumption, which is it is the probability of the number of independent occurrences in a fixed interval if these occurrences have known average rates. So suppose that you have customers arriving at some queue at a given rate. So on average, they arrive at this uniform rate of, say, 4 customers per minute. You may ask, what is the probability that in 15 minutes I get this number of customers arriving? And this is given by a Poisson distribution. So there's nothing, you don't need to assume anything about the process other than they're independent occurrences in a fixed interval with a fixed average rate. That's all you need to assume. And then you immediately get a Poisson distribution. And there are lots of things that follow Poisson distribution: raindrops, radioactive particle decays, number of calls per hour in a call center. This was from last or 2 years ago, number of tweets per day by Donald Trump, or many, many, many things follow Poisson distributions. Okay, continuous random variables. How do we deal with continuous random variables? Here the tool is different. So the thing that we need to handle is something called the probability density function. And the probability density function is just a non-negative function. So this red line, which when I integrate from minus to plus infinity gives you 1. And such that if I want to compute the probability that x belongs to some interval, say a to b, you need to compute the area under the curve here of this function. Integrate from a to b, this density. This is the sort of not a definition, but it's almost a definition of what the probability density function is. Notice that the probability of a given specific value is 0 if I have a continuous probability density function. The probability that x equals c is 0, because when you integrate from, say, c to c, any finite function, continuous finite function, will give you 0 because it's just a point. It's just a 0 measure set. So it's important. So a continuous random variable will have 0 probability of taking any specific value. What it doesn't have 0 probability is of belonging to some interval, but the interval needs to be non-zero. A needs to be different from B. Okay, important continuous random variables, the uniform. So I wouldn't even sketch it because it's clear what it is. So it's a flat function between 2 different points, A and B. And of course, the density needs to be 1 over B minus A, so that you integrate to 1. And the all-important Gaussian. So the Gaussian, which I'm sure most of you have seen and worked with, is given by that expression. So it's 1 over square root of 2 pi sigma 2, and then this exponential here. And it has this familiar shape, which you've all, I'm sure, seen. I'm not telling you right now what mu and sigma 2 are. In this case, they're just parameters that specify. So mu specifies the location of the function, and sigma 2 specifies the width of the function. So if sigma is large, you have a wider function. If sigma is small, you have a narrower function. And the location is specified by mu. So mu is the location of the function. Another continuous random variable, which is also very important, of course, is the exponential. So the exponential is for variables that are larger or equal than 0. So they have 0 probability of being negative. And they follow this distribution. So this density, it's just an exponential multiplied by whatever I need to multiply, so that I guarantee that when I integrate the function from 0 to infinity, I get a 1. So what things follow exponential densities? For example, the time that elapses between 2 arrivals in a Poisson process. So if you say, if you assume that some process is random, say customers are arriving at a queue at a uniform rate, if a customer arrives now, the distribution of the time it takes for the next customer to arrive follows an exponential distribution. And this is not for customers, for packets in a network, for raindrops, for particle decays, for many, many things. So important characteristics of random variables. So probably the most important of all is expectation. So how do you compute expectation of a random variable? So expectation of a random variable, you compute it depending on whether it's continuous or discrete. If it's continuous, you just sum the values, multiplied by their probabilities. You sum across all possible values that the random variable takes, and you get the expectation. This is the definition of expectation. If the variable is continuous, then rather than summing, you integrate x times the density, and you get the expectation. So for example, for the Bernoulli has these, so it's a coin toss with 0 for tails and 1 for heads, which is given by this probability mass function. So just by invoking the definition, I need to sum across the values 0 and 1, 0 and 1, multiplied by the corresponding probabilities. 1 minus p is the probability of 0, p is the probability of 1, and so I get simply p. So the expected value of a Bernoulli random variable is simply equal to the probability. This is a very general fact, which is sometimes useful, which is the expected value of a binary random variable. If you have a binary random variable, takes values 0 and 1, its expected value is simply equal to the probability that it's equal to 1. It's probability. Okay. For a binomial, for example, we can do the computation. I'm not going to do it, and we get n times p. What this says is that if you toss n coins, the expected value of the number of heads is the number of tosses times the probability of heads, which is what you would expect it to be. For a Gaussian, now I'm not going to do any computations. It's easy to derive. It's just need to do the integration, that the expected value is precisely parameter mu that appears in the definition of the Gaussian. And an important property of expectation is just it is linear, meaning that if you have a linear combination of two random variables, some alpha and beta are real numbers, alpha and beta multiplied by x and y respectively, then the expected value of this combination is the same combination of the expected values of the random variables. Okay, if rather than the variable itself, you need to compute the expected value of the function of the variable, all you have to do is replace the variable by the function in there. And these two expressions, so for discrete and continuous cases, is called the law of the lazy statistician, because although in fact you have another random variable here, which is g of x, you don't need to compute the probability mass function of these. You can just plug these into the expressions and you can do the computation. And that's why it's called the law of the lazy statistician. So for example, you get the variance when the function that you plug in there is x minus the expected value of x squared. Then you just get something which is called the variance. So this function g in this case is this squared inside. Which just by expanding the square, it can be simplified into the expected value of the square minus the square of the expected value. So for example, for the Bernoulli, we can compute the variance easily. Notice that in the Bernoulli, the squaring or not squaring doesn't make any difference, because the value x is either 0 or 1, and 0 squared is 0 and 1 squared is 1. So the expected value of x squared is the same thing as the expected value of x, and we already know that this is p. And so just by using this expression, we know that this now will be p minus p squared, which is the same as p times 1 minus p. And that's how we compute the variance of a Bernoulli variable. For the Gaussian variance, we need to compute the expected value of this square, because we already know that the expected value is mu, and doing the integration and so on and so forth, we reach that its value is sigma 2. I'm going to skip this. Okay, why do we pay so much attention to the Gaussian? Maybe you don't remember this because most of you are much younger than these, but the final edition of the Deutschmark banknotes had this Gaussian distribution in there, so it's probably the only mathematical expression that appears in a banknote. It doesn't appear anymore. Now we have euros, no more we have Deutschmarks. But this is a picture of Gauss, and so it must be really important, and the Gaussian must be really important to figure in a banknote. And it is, in fact, really important. And it's important for many different reasons. So I'm just going to briefly review one of them, which is if you have some random variable, I'm going to go fast. Of course, the slides and the video will be available. You can play it slowly. You can read about these in many other places. So suppose you have a collection of random variables that are independent. It doesn't really matter what their means are and what their variances are, as long as they're finite. And now suppose that you add them together, okay? Up to, say, you have n of them and you add them together. So because of the linearity of expectation, the expected value of the sum is the sum of the expected values. Let's call it mu. Same thing for the variance. Now, if you normalize for Zn, if you define for Yn, so after you sum n of them, If you normalize in the sense that you subtract the mean and divide by sigma, well, if you subtract the mean, you get expected value 0, because when you have a random variable with some mean, some expected value, and you subtract it, you get 0 expected value. If you divide by the standard deviation, you get a unit variance. Then it can be shown that if n is really large, then this random variable is approximately Gaussian, no matter what the distribution of these x's are. And so this is why the Gaussian is so ubiquitous, because many things in nature and in society are the combination of different factors. And if they're a combination of a large number of factors, and these factors are independent, then on average, the distribution will be not very far from Gaussian. It will have this bell-shaped curve, independently of what the distributions of the underlying factors are. And so this is a very relevant fact. So how do we deal with more than 2 random variables? We've been looking at how to deal with 1 random variable. Let's see how we can deal with 2 or more. Okay, and there's nothing different with the more. So 2 already captures the essence of dealing with more than 1. So we have the joint PMF, joint probability mass function of 2 discrete random variables. It's just the probability that one of them takes one value and the other one takes that other value. That's all. Okay, there was a question in the chat. There were maybe some typo in one slide. Okay, I'll come back to that in the end. Okay, so it extends trivially to more than 2. Of course, it's x, y, and z, and as many as you want. So for 2 random variables in the continuous case, the probability of x and y belonging to some set, so the pair belonging to some set, this subset A is a subset of R2. You just do it by integrating the density across this set. So there's nothing specific, nothing special about this. So one important concept when you have deal with more than 1 random variable is marginalization. Is how do you obtain the probability mass function in a discrete case or density function in the continuous case of one of the variables given the joint PDF or PMF. You just need to sum with respect to one of them or integrate with respect to one of them, depending on whether you want in dealing with discrete or continuous. This is called marginalization. And we say that 2 variables are independent. Now we're talking about random variables, not events. So we say that random variables x and y are independent if and only if the joint probability mass function or density function, so this is definition, it doesn't matter whether we're dealing with discrete or continuous random variables. So it's when the joint density or mass function is the product of the marginals. It's important to keep in mind that this, of course, implies that the expected value of the product is the product of the expected values. But the fact that the product of the expected values equals the expected value of the product does not imply independence. So this is an implication in one way, but not in the other way. So for these to imply independence, we need to add more conditions to the distributions, to the densities or mass functions. Okay, Bayes' theorem as seen for random variables. For the discrete case, it's direct application of the Bayes' theorem for sets. It's just a joint probability divided by the marginal. And these are all probabilities, because when we have conditional probability mass functions, what we have here are probabilities. It's probability that big X equals little x and big Y equals little y, and the probability that big Y equals little y. No problem about that. But when we're dealing with conditional probability density functions, it's still true that the conditional density of x given y equals the joint density of x and y divided by the marginal density of y. But the meaning here is technically delicate, because what we have in the denominator is not a probability, because the probability of a given value is 0. This is a density. And so the meaning, technically, these 2 things are, although they look exactly the same, they are slightly different in terms of technical support. So finally, Bayes' theorem, which is how to go from y given x to x given y, is exactly the same shape, independently of being a PDF or a PMF. It's probability of y given x times probability of x divided by probability of y, or density. This could be densities or probabilities. It doesn't matter. Okay. This is also valid in the mixed case. You can have, say, x being continuous and y being discrete, or vice versa, or so all combinations of PDFs and PMFs are valid in expressions of this form. Okay, I could spend a few seconds just illustrating these, but this would be really probability 101. Let me see what time it is. So I'll probably, well, this is very quick. So if you have a pair of random variables that are binary with some joint probability mass function, so the probability that y equals 0 and x equals 0 is 1/5, and this is for the other combinations. How do you marginalize? So you marginalize by summing across rows if you want marginal in x, or summing across columns if you want marginals in y. And then how do you get conditionals? By taking these joint distributions and dividing by the corresponding marginals. So you either normalize columns if you want probability of x given y, or you normalize rows if you want probability of y given x. So essentially conditioning, going from joint distributions to conditional distributions, simply amounts to normalizing in the right way. You want to normalize rows, or you want to normalize columns, or in the continuous case, you want to normalize cross sections of the space. An important, very important multivariate random variable, and we'll see about two of them, is the multinomial. So the multinomial is sort of a generalization of the binomial. I just said generalized binomial for more than two classes. So you can think of the binomial of the number of heads you get when you toss a coin n times. So you can think of the multinomial as the number of 1s, 2, 3, 4, or 5, or 6s that you get when you toss a die n times, or when you toss n independent dice. It's the same. Where probability P1, P2, say to P6 would be the probabilities of each of the faces of the die. X1, X2 to X6 would be the number of ones, number of twos, number of all the way to 6. And this factor here that you get, this combinatorial term, which is called the multinomial coefficient, just counts in how many ways out of n tosses you can get x1 of 1s, x2 of 2s, all the way to xk of k's. Of course, under the constraint that the sum of these xi's needs to be n, right? Because if you toss a die 20 times, the number of ones plus the number of twos plus the number of threes and so on needs to add up to 20, because the die, you didn't lose the dice and you didn't create new dice. So this is what I just said. This is a very important model. It's at the heart of a classical and old model in NLP called the bag of words, which sees words as being generated randomly from a multinomial distribution. Another very important multivariate, of course, is in the continuous case, is the Gaussian. So the Gaussian goes as this shape. I'm not going to go into details about the shape. Why is it important? Well, I will see in a second. So notice just that it's parameterized by some parameter vector mu and some matrix C. So C is a matrix. Its expected value is mu, and the meaning of C we'll see in a second. So it has this familiar shape. This is in 2 dimensions. So for n equals 2. And mu controls the position, so just the location, but not the shape. The shape of the density is controlled by this matrix C, which you have seen before, I'm sure. So the main reason why the multivariate Gaussian is important is because of this closeness, this property, which is if you have a Gaussian, if you have 2 random variables which are Gaussian, the marginals are still Gaussian. This is very important because when you start with Gaussians, you only have to deal with Gaussians all the way to the end. So Gaussians have this very important property, which translates, of course, into conditionals too. So if you have a joint Gaussian, the conditional density of one of the variables given the other, or the conditional density of a subset, if you have 10 variables which follow a Gaussian in 10 dimensions, the conditional density of some of them given the others is still Gaussian. Everything is still Gaussian. So when you're dealing with Gaussian, you stay in the Gaussian world and everything is Gaussian. And everything can be computed in closed form, which is why the Gaussian is so important. And we always try to deal with Gaussians whenever possible. What about transformations? I'm going to skip this slide. So this slide is about, suppose you have a random variable of which you know the density, and you transform it by making it go through some function g. What is the density of the result? I'm not going to talk about it in detail. I'm just going to say that you need to know the derivatives of Jacobian if this transformation is multidimensional. And you need to know this if you deal with generative models, if you deal with, say, normalizing flows or VAEs or all these probabilistic models. This is a very important topic to know very well. how random variables are transformed through functions. Okay, covariance, correlation, and all that. Correlation and all that. So what is if you have two random variables, the covariance between these two random variables is the expected value of the product of two things. One of them minus its expectation, the other one minus its expectation, which can also just by doing these multiplications and using the linearity of expectation can be written as the expected value of the product minus the product of the expected values. So the variance of a random variable is just the covariance of it with itself. Notice that if x and y are the same, this is e of x squared minus e of x squared, the square outside. We can normalize it by dividing by the square root of the variances, and we get something which is called the correlation. The correlation now is between -1 and +1 because we're normalizing by the variance. I'm not going to show why this is between -1 and +1, but it is. We say that two random variables, we already saw these, are independent if and only if the joint density equals the product of the marginals. And I'm showing this just to show this implication. This implies that the covariance is 0, but the fact that the covariance is 0 does not imply that they're independent. So it's important to keep in mind. Sometimes we say uncorrelated to mean independent, but that is wrong. So uncorrelatedness means correlation is 0. Correlation is 0 does not imply independence. This is only true, well, roughly if they're Gaussian. If they're not Gaussian, this is not true. So what about covariance matrix? If you have more than two, say n, you can write compactly this covariance of x. It means the expected value of x minus its expected value times the transpose of this, okay, which is a matrix. It's an n by n matrix, which can be written like this. Okay, this, if you don't know it, it's hard to explain in a second, but this is important, very important thing to know about Gaussians. What about some properties of expectations which are used on a daily basis in these areas? So if you have an expectation variable that has expected value mu, and if you have some linear transformation, so if y is another variable that is matrix A times x, then just because of linearity of expectation, the expected value of y is A times mu. So this is a fundamental property. Another thing is addition. So if you have a random variable that has expected value mu, and you have another random variable y, which you get from x by adding some vector gamma, then the expected value of y is just mu plus gamma. So you can shift or multiply expected values. What about the covariance? So if you have some variable x that has covariance c, if you do this same transformation, y equals ax, then the covariance of y is a times c times a transpose. So all of this is easy to compute. This is just a particular case. And a particular case of these is if you choose A to be the inverse of the square root of C. So a matrix that when I multiply it by itself, it gets the inverse of C. Then in this case, the covariance of Y is simply identity. So if you combine the second and the fifth fact, so the second and the fifth fact, this is known as standardization. It means that you have an expected value mu and covariance C. If you do this transformation, if you subtract the expected value and you pre-multiply by the inverse of the square root of the covariance, you get something which has 0 expected value and identity covariance, which is called transforming some random variable which is Gaussian or not. This is not about Gaussians. If you have a random variable that has some mean and some covariance, this transformation produces a random variable that has 0 mean and identity covariance. And if you combine the second and the third facts, it's going the other way around. It's going backwards in this transformation. It just says that if you have a random variable x that has 0 expected value and identity covariance, if you multiply it by a and add mu, then you have another random variable with expected value mu and covariance A transpose. And this is called the reparameterization trick in generative models, because you reparameterize a variable which you need to have some covariance and some expectation. You simply parameterize it using the multiplication and an addition with another random variable which has a fixed expected value and fixed covariance. I will probably keep this slide and this slide. You can read about it later. Yep, I will. Okay. Important inequalities. So inequality is a very important area in machine learning, especially in theoretical machine learning. So I will talk just briefly about inequality. So the mother of all inequalities, sometimes it's called well, some people call it to Markov's inequality, because a lot of inequalities can be derived from this one, which is quite simple. And it states the following: if I have a non-negative random variable, which has some expected value e of x, then the probability that this variable is larger than t is less or equal than the expected value divided by t. Okay, this is easy. This is easy to understand what this says. It's not easy to understand why this is so. It's a proof that I'll show in a second. It's a one-line, very simple proof. But it just said if you have a random variable that has expected value 3, and it's a positive random variable, what is the probability that the variable is larger than 7? It's 3 over 7. It's less than 3 over 7, no larger than 3 over 7. And the larger t is, the less the probability becomes. And all you need to know this bound is the expected value and this value t that you want to compute the probability that x is larger than. How do you prove this? It's extremely simple. It's just this. I'm not going to show. I'm not typically don't show proofs here, but this one is absolutely simple and nice, and it captures the essence of what proofs typically are in this area. So you start by writing, you take this t and move it here. So what I'm writing here is this t on this side here. It's t times the probability that x is larger than t. So the probability that x is larger than t would be the integral from t to infinity of f of the density. But I have a t outside, I can move it inside. It doesn't hurt because it doesn't depend on x. So now, of course, this is less or equal than, this becomes larger than this if I replace t, which is fixed at the lowest value, if I replace it by x, because x will go from t to infinity. So this side is, of course, larger than this side. Now, if instead of integrating from t to infinity, I was integrating from 0 to infinity, this would be by definition the expected value. But it's not, because I'm integrating from t to infinity. So this is the expected value minus what I left out, which is the integral from 0 to t. So this is minus 0 to t, this function. But this, of course, is larger or equal than 0 because densities are larger or equal than 0, and x is larger or equal than 0 because it's somewhere between 0 and t. So this is larger or equal than 0. And so if I remove it, I get something which is larger or equal, which is, by definition, e of x. And that's it. Now you take this t, you move it here, divide by t, and you get the Markov inequality. So the Chebyshev inequality, which is a well-known inequality too, which says that the probability that the absolute value of the difference between some random variable and its expected value being larger than s is upper bounded by the variance divided by s squared. And this can be proved simply by a certain choice of what x and t are and plugging them into Markov's inequality. There's another inequality, which I haven't talked about. We will talk about in a second, which is called Cauchy-Schwarz, which is for vectors, for vector spaces, from which we can prove that, I'm not going to prove it here, but you can prove that the expected value of the product, of the absolute value of the product of two variables, is upper bounded, is less or equal than the square root of the expected values of the squares of these two variables. And from these proof, from this, you can actually show that the correlation is between -1 and +1. But I'm not going to show this. So a very important concept, which will be used, is very central in machine learning, is that of convexity, of convex functions. So visually, it's very simple to understand what a convex function is and what a non-convex function is. So essentially, a convex function, a univariate function, is convex when I take 2 points on the graph of the function and I join them by a straight line. This straight line does not cross the graph of the function. So this is a convex function. This is not a convex function because this line crosses the graph of the function. So formally, implies is that the function computed at any point between x and y, given 2 points, say x and y, alpha x plus 1 minus alpha y is called a convex combination of x and y. So when alpha goes from 0 to 1, this point alpha x plus 1 minus alpha y travels from x to y. It means that this function g computed at any point between x and y is less or equal, means this blue line is less or equal than the same combination of the two values. So this is the height of this straight line. So this is a straight line that goes from g of x here to g of y there. Okay, so this is a mathematical expression that this straight line stays above the graph of the function. And so we need this definition to use to state this famous Jensen's inequality, which says that if g is a real convex function, then the function computed at the expected value is less or equal than the expected value of the function. And this is at the heart of a lot of modern machine learning, namely the famous evidence lower bound, the elbow, all of variational inference, all of variational autoencoder, all of variational inference is based on this inequality, on instances of this inequality. So this is important, very important to know. Examples of these are, of course, the square, x squared is a parabola, is of course a convex function. And so we know that e of x squared is just this, is less or equal than e of x squared. And this is just another way of saying that the variance is larger or equal than 0, which you already know, because e of x squared is larger or equal than e of x squared. The log, for example, is not a convex function, it's a concave function, because minus log is convex. And so in this case, the inequality is reversed. So its expected value of log is less or equal than the log of the expected value. And this one, yes, is at the heart of variational inference and a lot of information theory. Okay, let's look a little bit at information theoretical concepts. So information entropy and all that is also play very important roles in modern machine learning. We talk about entropy a lot. And so entropy is another fundamental concept that I think should be taught to everybody that studies things that have to do with data and information, not only machine learning and electrical engineering and computer science. So entropy of a discrete random variable. So you have a discrete random variable that takes values, say, from 1 to k with probability mass function fx. So the entropy is just minus the sum of the probabilities times the logs of the probabilities. Okay, and it can be shown. It's very easy to show, actually. Sorry, getting some water. That it is a non-negative quantity. It's obviously non-negative because the probabilities are less or equal than 1. So the logs are negative. With the minus, it cancels out, becomes positive, and the probabilities are positive. So everything is positive. This one is not so easy to show, but it's true that for these to be 0, for the entropy to be 0, you need to have one possible outcome with probability 1, and all the others with, of course, with probability 0. So because of these, and because of the fact that the entropy is upper bounded by the log of the number of possible outcomes, and for it to be equal to the number of possible log of the number of possible outcomes, you need to have a uniform distribution, which you can argue it's the highest uncertainty, highest randomness in X. The entropy for discrete variables is often used as a measure of uncertainty or randomness. You have high entropy if you have a highly uncertain situation where you have a random variable about which you know nothing. You assume that distribution is uniform. Whereas in this case, when you know that one outcome has probability 1 and all the others have probability 0, there's no uncertainty at all because you know exactly what will happen. And so there's 0 uncertainty, 0 randomness, 0 entropy. The typical log that we use there is log base 2, and in this case, the units of this quantity of entropy is sometimes called bits or bits per symbol, if you think of these as symbols, or bits per outcome. This has a central role in information coding theory, of course, in many areas. So the entropy is widely used in many areas. Of course, it's a concept that comes from statistical physics, and it's used in many other areas. What about continuous random variables? For continuous random variables, the definition of entropy mirrors the one for the discrete case, but instead of a summation, here you have an integration of a density. But unfortunately, this is not the same type of object. Now it's no longer called entropy, it's called differential entropy. And it loses one of the main important properties of the entropy for discrete variables, which is this is no longer guaranteed to be larger or equal than 0. For example, if we have a uniform density, it's very easy to see that if you have a uniform density where the density is 1 over b minus a, and if you compute the entropy, the differential entropy, by integrating from a to b, this quantity, it's just one line to show that the differential entropy is log of b minus a. But since we not imposed any condition that b minus a needs to be larger than 1, b minus a can be less than 1, it can be 0.5 or 0.1 or whatever you want, for it's still a valid density, this log can be negative. And so it's no longer true that this is a positive quantity. So it loses the notion, it loses the meaning of the number of bits, for example, to express a variable. It's a different kind of object. So there's yet another reason why the Gaussian is important is that it has this very important relationship, which says that if you have a density, a Gaussian density, the differential entropy of the Gaussian density is this beautiful expression that involves all the important numbers of math. So 1, 2 pi e. So it's 1/2 of the log of 2 pi e sigma 2. So it depends only on the variance. It doesn't depend on u, on the location. It can be shown that if you have a random variable with a variance sigma 2, then this variable, no matter what the density is, cannot have entropy larger than the entropy of the Gaussian, meaning that the Gaussian, among all densities with the same variance, is the one that achieves the highest entropy, differential entropy. And this is yet another reason why the Gaussian is such an important variable. Okay, Kullback-Leibler divergence. The Kullback-Leibler divergence is a quantity which is closely related to the entropy. Sometimes it's called the relative entropy. And it measures the similarity between two probability mass functions. So you have two probability mass functions, f and g, let's say. You compute their Kullback-Leibler divergence by computing this expression, by summing across the possible values, f times the log of the ratio between f and g, okay? And it can be shown that this is always larger or equal than 0. It's not obvious. It's not at all obvious. You need to invoke, to prove this, you need to use the fact that log is a concave function, and you need to use Jensen's inequality. I'll skip any more comments. And it can be shown that so it's larger or equal than 0, and for it to be equal to 0, you need to have f and g being equal to each other. And so this is why it's used as a measure of how different two distributions, to probability mass functions are. In the continuous case, instead of a summation, you have integration. So you integrate rather than summing because you're dealing with densities. But interestingly, it's still true. So unlike in the entropy case, where the entropy for the continuous variables is not guaranteed to be larger or equal than 0, it can be negative. The Kullback-Leibler divergence between discrete or continuous random variables has the same properties. It's always larger or equal than 0. And for it to be 0, f and g need to be equal to each other. There's a technicality in the continuous case because they don't need to be equal everywhere. They only need to be equal to each other almost everywhere because of the integration and blah, blah. But essentially, in essence, they are essentially the same object, regardless of whether you're dealing with continuous or discrete random variables, because of these two properties. The properties are maintained when you go from discrete to continuous. Notice, for example, notice also that this is not a symmetric quantity. So if you swap f and g, you don't necessarily get the same quantity. For example, if g is 0 at some little x for which f is not 0, you get infinity because one of the terms in the sum is infinity. Some finite number divided by 0, you get log of infinity is infinity. But if you swap them, this may no longer be true. And so this is not a symmetric quantity, and there are symmetric versions of these when you compute, say, the average of dfg plus dgf. And but it's important to know that it's not a symmetric quantity. What is what we call the mutual information between two random variables, which is another important quantity in information theory and in inference, is the Kullback-Leibler divergence between the joint density or mass function of these two variables and the product of the marginals. Remember that if they are independent, these two things are equal. That's the definition of independence. And if these two things are equal, then the divergence, the Kullback-Leibler divergence is 0 and the mutual information is 0. So the mutual information measures how far from independent two variables are by measuring how different the joint distribution is from the product of the marginals. It is positive, larger or equal than 0. Why? Because this is a Kullback-Leibler divergence, and we know it's larger or equal than 0. And for it to be 0, we need these two quantities, these two functions to be equal. And for this, if these two functions are equal, the variables are independent. It's the definition of independence. And so in between, you have from 0 to whatever the maximum value it is, you have a measure of dependency. So you have a measure of dependency between two random variables. And actually, if you're using log2 in the computation of the Kullback-Leibler divergence, this is exactly, it has a very clear meaning. It's the number of bits of information that random variable X has about the other random variable Y. It's a measure of how much you know about a variable by knowing another variable, how much a variable knows about another variable. It is upper bounded by D, so the mutual information between two variables can be no larger than the minimum of the two entropies of the two variables. Why? Simply because no variable can have more information about another variable than it has about itself. It has all the information that it needs to have about itself. It cannot have higher information about another variable than it has about itself. So the mutual information between two variables can only go up to one of the two, the information that the two that has the least information about itself has about itself. An extreme case of this is if one of the variables is a function of the other, okay, and I'm talking about discrete variables. If one of the variables is a function of the other, then the mutual information is simply the entropy of this variable, which is less or equal than the entropy of X. It's equal if this function is bijective, is less if this function is not bijective. So for this probability theory part, this is what I recommend as reading. This is what I recommend to my students to get ready for machine learning courses, is essentially the first chapter, the first actual chapter of Kevin Murphy's book, Machine Learning, a Probabilistic Perspective. There's a new version, the new edition, it's coming, it's already available online if you want to search for it. It's publicly available if you search for Kevin Murphy book. I also recommend this Larry Wasserman's book, All of Statistics, Concise Course in Statistical Inference. It has almost everything a machine learning person needs to know about statistics. And there's a nice little review by Aryan Maleki and Do. This is from one of the Stanford machine learning courses. This is the refresher probability theory course. Okay, so I have a second part about algebra and a few other things, which in the interest of time, I'm gonna fly over. I'm just gonna tell you what it covers. And I'm gonna tell you, I'm not gonna go over the topics. I'm just gonna tell you what I think anyone who works in machine learning or wants to study machine learning needs to know. So don't see this as a warm-up or a refresher, but just as a sort of list of things. So of course, you need to be extremely comfortable with matrices. You need to know exactly what a matrix is, the rectangular box filled with numbers. You need to know what a vector is. You need to know that vectors are just particular cases of matrices. And of course, you need to know that column vectors and row vectors are just matrices with one column or with one row. You need to know what a transpose is. You need to know what a symmetric matrix is. You switch columns by rows in the matrix. You need to know what products of matrices mean. You need to know that when you multiply matrices, they have to have certain agreement between their dimensions. So you can only multiply a matrix that has the number of columns is the same as the number of rows of the other column. Otherwise, you cannot multiply them. I'm not going to explain why. You need to know that the inner product between two vectors is a particular case of a product between two matrices. It's a row matrix times a column matrix. And that's an outer product between two vectors is again another type of product between two matrices. In this case, a column vector by a row vector. You need to be very familiar with all the properties of matrix products. So it's associative, but it's not commutative in general. That the transpose of the product is a product with transposes, that the transpose of the sum is a sum of the transposes. You need to know all these. You need to be familiar with special matrices such as identities. You need to know exactly what an identity is. It's a neutral element of matrix products. You need to know what diagonal matrices are, matrices that only have elements along the diagonal, but this is the diagonal, these elements here. If everything else is 0, then you have a diagonal matrix. You need to know what an upper triangular matrix is, what a lower triangular matrix is. So only values above the diagonal or below the diagonal. This is very important, for example, in normalizing flows. You need to know very well what eigenvalues are. So there's a lot of talk about eigenvalues, even, of course, in deep learning. So an eigenvector and an eigenvalue of a matrix are, so the vector, if you have a vector such that when you multiply it by the matrix, it's the same as multiplying by the scalar lambda, then you say that this is a eigenvalue and X is an eigenvector. You need to know what the trace is, the trace of a matrix, the determinant, all of the properties. So the trace is the sum of the elements along the diagonal, which is also equal to the sum of the eigenvalues. The determinant is, it's not by definition, but it's equal to the product of all the eigenvalues. The determinant appears in the computation of the inverse of a matrix. You need to know properties of the determinant. All of these you need to be very familiar with, that the determinant of the product is the product of the determinants. The determinant of the transpose is the same. All of these properties you need to be aware of. So, for example, these which I'll skip. So you need to be very familiar with inverse, what the inverse of a matrix means. It's a matrix that when you multiply by the other matrix, you get an identity. So it's a neutral element. You need to know that the matrix to be invertible, you need the determinant to be non-zero. You need to know all of these properties of the determinant. You need to know why inverses are important, namely because they allow you to solve linear systems of equations. You have a linear system of equations expressed in matrix form. You solve it by multiplying on the left by a minus 1, because a minus 1 times a is identity. You get x equals to a minus 1b. You need to know that the inverses of inverses are the same. So, and the inverse of the product is the product of the inverses in reverse order. You need to know we've written quadratic forms when talking about Gaussians, what quadratic forms are. So quadratic form involving some matrix A is the sum across all the elements of the matrix multiplied by the corresponding components of X. So you see the expression, the sum across from 1 to n of all the elements of the matrix times xi, xj. This is called a quadratic form. And we say that this matrix is positive semi-definite if this is always larger or equal than 0, no matter what x is. And you say it's positive definite if, as long as x is not 0, then this is strictly larger than 0. And this is how it relates to eigenvalues of the matrix. So you need to know all of these. This is things that are assumed knowledge if you're a student of machine learning. Of course, I'm not assuming that you know all of these, but I'm saying that, and I'm not, of course, even less assuming that you're learning now, but this is important stuff. So you need to have some familiarity with what vector spaces are, especially if you want to do a bit more theoretical work. You need to know about properties of vector spaces, which I will not go into right now. You need to know what these are examples of vector spaces. So the standard examples are important, say vector in Rn, which you're familiar with, I'm sure. Matrices are elements of vector spaces. Complex matrices, of course. Binary vectors are also elements of vector spaces. Functions, you can also define functions as being elements of vector spaces, and so on and so forth. You need to be familiar with norms, what a norm is, what properties a norm needs to satisfy, namely the triangle inequality and definiteness. That you only have a 0 norm if you have a 0 vector. This is a very important property of norms. The homogeneity, that some scalar times a vector, the norm of this product is the absolute value of the scalar times the norm of the vector, and the triangle inequality, which maybe I'm sure you're familiar. You need to know some examples of norms, namely the Euclidean norm. You need to know the notion of equivalence between norms, which I will not state. Examples of norms, say L2, L1, which is the sum of the absolute values, L infinity, which is the maximum absolute value of the components of a vector, and the L0, which is not a norm, which is the number of elements that have non-zero value. This is sometimes called the zero norm, although it's not a norm. Okay, you need to be very familiar with inner products, what properties an inner product needs to satisfy. Standard inner products say that lead to the Euclidean norm and the Mahalanobis norm. Key products of the inner product. So this property, the Cauchy-Schwarz inequality, which it's a fundamental property of inner products, is the key. I'd say this inequality is the cornerstone of, I don't know, maybe 50% of all the proofs of theory in machine learning. These, together with Jensen's inequality and Markov's inequality, with these three things, you can prove almost anything. These are really, really the bottom of the properties that we deal with when proving things about statistics and probability and machine learning. I'm not going to show you the proof. There's a one-line proof in the slide. You can read it later. Okay, basis, what's the notion of a basis? So a basis is a collection of linearly independent vectors. I'm running out of time. Yes, I am. I'm just going another 5 more minutes. So I'm going to skip this. So the base of the normal basis. For matrices, you need to be very familiar with these notions of rank, range, and null space. So the range of a matrix is the space of all the vectors that you can produce by multiplying this matrix on the right by some vector. So it's everything that you can generate by writing AX when you change for different choices of X. The null space is the collection of vectors such that when you multiply by A, you get a 0. Okay. So these are both vector spaces. It's easy to show that they're both vector spaces in the sense that if you sum two vectors that when you multiply by X gives you 0, of course the sum also gives you 0 and so on. There's a very, very important dimension theorem that has the dimension of the range plus the dimension of the null space is n, number of columns of the matrix. That the rank is the dimension of the range, which is always less or equal than the minimum of m and n. And from this you can show this. And finally, and I think this is almost the end, we have this central tool in linear algebra, which is a singular value decomposition. There's something called the singular value decomposition theorem that says any rank R matrix, any matrix of some dimension that has rank R, remember what rank is, so rank is the dimension of the range space, can be written in this factorized form as there's a diagonal matrix here that has something called the singular values. There's an orthonormal matrix on the left, an orthonormal matrix on the right. These have orthonormal bases of the range of A and of A transpose. I'm assuming that, just saying that you should know these. If you don't know, you need to look it up, not necessarily today, of course. The singular values are the square roots of the eigenvalues of these matrices. Notice that a general matrix, if n is not equal to n, does not have eigenvalues, but A transpose A or A transpose are square matrix. This is square matrix. This is a square matrix. So these do have eigenvalues, which are called the square roots of these eigenvalues are so called the singular values. Orthogonality of U and V mean these. So this matrix U transpose U needs to be identity, and V transpose V needs to be identity. This essentially means that the columns of U are orthonormal vectors. And if you want to transpose, if you transpose these, you use the property that the transpose of the product is the product of the transposes in reverse order. You can write it in this way. So visually, what the singular value decomposition tells you is that any matrix n by n that has some singular values here, which are the eigenvalues of A transpose A, can be factorized in this way. There's this matrix that has as many columns as A has and as many rows as the rank of A. Then you have this little matrix here, which is a diagonal matrix R by R. And then this tall matrix here, which has as many columns as the rank of A and as many rows as A. And this is I have a colleague in the University of Medicine that once, for several years, taught a machine learning course only using the singular value decomposition. If you don't go into deep learning or in other topics, you can talk a lot about machine learning just using singular value decomposition. There's a lot of important algorithms in machine learning that can all be seen as applications of singular value decomposition. If you want a more graphical representation of what the singular value decomposition says, is the following. So when you multiply vectors by some matrix, essentially you're rotating and rescaling the vectors. So if the product of m times this red arrow is this red arrow, the product of m by this yellow arrow is this yellow arrow. What is the singular value decomposition says is the following. This is equivalent, this product, this operation is equivalent to first rotating the vectors, then rescaling the space. This is when you multiply by a diagonal matrix, you're rescaling the x and y axis according to the values of the singular value. So you rescale the space, you shear the space in this way. So you stretch it horizontally, and maybe you shrink it vertically, depending on what the singular values are. And then you undo the rotation by multiplying by u. And so this is what the singular value multiplication does. So convex sets I will jump over. Convex functions we already saw in the first part of the talk. And so I leave you with recommended reading about this part. So again, from in the same machine learning course at Stanford, which you have the link there, maybe it's there's an updated version now. There's this review of linear algebra and reference, which covers most of what I've said it is important. And so these are nice reading elements for you to refresh your knowledge about math and these topics of math. Okay. Thank you for attending. I hope you had your brains warmed up, or maybe you felt really comfortable because you already knew all of these. If you don't know any of these, you should know at least, you should go and study some of these. And you can use these as a, I think you can use these slides as a list of things that you should study more in detail. Of course, this is not a detailed lecture. This is more an exhaustive overview of topics that are important as background for machine learning. And but of course, I'm happy to take any questions if you have them. And with these, I thank you all. Okay, I don't know if there's Fernando is there.
There were two questions. More in the beginning of the class, of the lecture. So the last one was, how do you relate the expected value with like a real world example?
So an example I gave was, for example, if you're tossing, suppose you have a coin that you know is biased, and it has a probability, say 0.6 of giving you heads, and you're going to toss it 100 times. What's the expected value of the number of heads it will gives you? It's p, not 0.6, say, it's biased, times 100, so it's 60. So the expected value is the value that you expect to get when you do the random experiment. There's no other way of saying it. It's not necessarily the most likely value. It's not necessarily the value that is most likely, that has the highest probability, but it's the expected value. For example, in an exponential density, if you have an exponential, this is a misleading, sometimes a confusion, which is that confusing expected value with the value with the highest probability, which is not. Suppose you have a density, an exponential density, which, suppose you arrive at a train station, and it's a very strange train company where the trains arrive randomly, following a Poisson distribution. So the trains arrive randomly, which is not, of course, true, right? So here, if the trains arrive randomly, the distribution of the time you need to wait until the next train arrives follows an exponential distribution. The longer you wait, so you have a high probability of waiting nothing, and a lower and lower probability of waiting, like 1 minute, 2 minutes, 3 minutes, 4 minutes, whatever this axis is. So the most probable value in this density is 0, which is the next train arrives right now, but that's not the expected value. The expected value is actually 1 over lambda, which is, in the case of, for example, for this purple line, it would be 1. So the expected value is 1. which is different from the most probable value because you need to integrate. Okay, so there are many thank yous. There was another question. Yes.
There was another question about some applications of concentration inequalities, like the Markov and the Cheryshev.
Yeah. So what is that? Okay. So a lot of theoretical machine learning, especially in the statistical learning theory, is about proving bounds that relate what you see in the training error with what you expect to see in expectation when you use the whatever you learned on new data. Okay, and to bound this deviation, you need to use concentration inequalities, and most, not all of them, but most concentration inequalities, McDermott and many others, are essentially derived from using Markov's inequality on different configurations. I gave an example with the Chebyshev. So you massage your inequality in such a way that you can bring it back to the form of Markov's inequality, and then you apply Markov's inequality. Although there are other tools, this is not general, but so that's the classical thing.
I think there's also a question about an intuition for a wide entropy of a random variable. P of x times log of P of x is the average level of the information or surprise.
Yeah, so that's nice. Well, I don't need to show it maybe, but okay, I'll show it not too far. Okay, this. Okay, so you can actually write these. Let's see if I can write. You can write these as. Can I annotate? Let me see if I can annotate. Yeah, you can write. I need to erase. Sorry. You can write these because if you look at these, you see that this is exactly takes the form of a sum of probabilities times some function. Okay, so you can write these. The entropy you can like this. You can write these as the expected value of minus log of f x of x. Okay, so the entropy can be written like this. And each of these, so what log of f of x is sometimes called a surprise, or minus log of f of x. So this is the same as log of 1 over f of x. It's called a surprise, meaning that if the probability is small, this is a large number, right? Because the probability is less than 1. So if you have a small probability, say 0.01, the log of 0.01 is minus something, minus 10 or whatever. And so with a minus, you get to 10. So an outcome with low probability has a high surprise. An outcome with a high probability has a low surprise. And so the entropy is, in essence, the average value of the surprise that you get when you observe the outcomes of the variable. So if you have a small surprise, you also have a small probability. So events with small surprise also have small probability of occurring, so they enter with a small weight in the average. And so the combination of these two, so this is a tricky, so this is a very particular, an instance of a very particular case of an expectation, where the function value, the probability mass function enters into place. It enters implicitly when you're computing expectations, because you need to sum, but it also enters as the function of which you're computing the expectation. Okay, and this gives it this self-referential kind of flavor that you're computing an expected value of a function of the density itself. And so this is it. So so minus log of f can be seen. So you can look at these as this is the same as log. When I teach these, I say that journalists and people who write newspapers know very well about these. Only surprising events have a lot of information. You don't care about things that are expected. So this is the same thing as this, right? Log of 1 over f of x. And so when probability is small, 1 over probability is large, log is large. So you have a lot of surprise, a lot of information when something improbable occurs. I hope that answers the question.
How would you measure the similarity between data sample points and the distribution?
Yeah, you can one sample point. You can measure the Kullback-Leibler divergence between sample points and the density by using the Kullback-Leibler divergence, but only in one direction. You can use if you have a collection of points, you can think that you have a density, which is a collection of masses, one at each observation. If you want to deal with, so there's a technicalities here, because if you want to compare points with a continuous density, then you need to write this mass as a collection of delta functions. And then you need to use integration of deltas. So you need to use integration of a function which is a collection of deltas times the log of this collection of deltas divided by the density. And if you look carefully at these, this is essentially the log likelihood function. Actually, this is the log likelihood function up to an additive term, which is the entropy of the observations. But you can do it. There's no problem. The only problem is that you can only do it in one direction. You cannot do it of the density with respect to the points, because the points have zeros, and so this would immediately go to infinity. You have to do it of the points with respect to the density. Just directly, you can directly apply the Kullback-Leibler of the point mass density with respect to a density, and no problem. It gives you if you know what it is, the log likelihood function plus a constant.
And could you give an intuition behind the use of entropy for the divergency in the cross entropy loss?
Well, the intuition is actually you don't have to use the log there. You can use other concave functions as a general. So this one is only a particular case. So here, let me see. Why is it moving? No, it's moving. Well, I needed to erase that. Actually, you don't need to use the log here. You can use any concave function, and it's called f divergence. Okay. For any other concave function that you put here, you get most of the properties, not all of them. So when you use the log, this has a very interesting and very strong and deep connection with coding, with information theory, because now it becomes, well, it connects directly with when you use these log, the log here, especially log 2, and then you use these to compute mutual information, then in the end you recover these property, number of bits of information that X has about Y. Okay. If you use another thing that's not a log, then you lose this connection. Okay. Another important thing is that the entropy in information theory, you can show that the entropy is, well, asymptotically, but that's not critical. The entropy tells you how many bits you need to encode samples generated according to this probability. And if you, for some probability mass function, and if you use another mass function, and you build a code using a wrong mass function, let's say, the number of additional bits that you pay, the loss that you incur in terms of wasted bits because you have the wrong distribution, the number of additional bits that you use is exactly given by this. So it's given by the Kullback-Leibler divergence between two densities if you use logs here. Okay, that's okay. So there's this connection with bits and information theory if you use logs. If you don't want to use logs, if you want to use some other concave function, this is still true. This is still true. But you have other properties that don't connect with information theory. So the main reason to use logs is because of information theory. And because it connects with exponential families, and because computing derivatives of logs is nice, and because computing the inverse of the log is the exponential, and when you're optimizing this stuff, it's nice to have exponential of things. So there's also a lot of underlying mathematical convenience reasons which are not explicit when you use them, but there are also those.
Do we have time for another question, or maybe?
Yeah, well, it's up to Fernando. What do you think? It's probably
maybe one last, because
more, yeah,
we are getting late.
Okay, so there's a question about using the Jacobian because it's useful for optimization, but it's hard to compute sometimes. So where is it used and not used, even the difficulties in computation?
So, well, this is a more technical question. And so I flew over the Jacobian, so I didn't want to talk about that. But so it's we use the Jacobian when we want to know how a variable is transformed by some mapping. And there's a lot of in modern machine learning. There's all these generative models, and some of them, one of the ones that's popular in recent years, called the normalizing flow, which is you have some network, you have some say Gaussian variable that you want to transform such a way that the density has at the output has some form that you will need to learn from data. And the main difficulty, the bottleneck, computational bottleneck in learning these structures is computing the determinants and optimizing the function, knowing that you will need to deal with the determinant. And so there's a big effort in trying to come up with transformations such that computing the determinant is computationally easy. So there's no general rule, it's just tricks. So there are different ways of composing several functions such that the Jacobian of each of them is easy to compute, and then the composition of the different functions is also easy to deal with. So there's nothing much more that I can say without writing down stuff. And but I can if you're interested in something, if you email me offline, I can say a few more things.
Okay, thank you very much, Mario, for the great presentation. I believe that we are running late, so I propose to start in 15 minutes, maybe 11:10. What do you say? Okay, let's do a small break, 15 minutes break, okay? We will start 11:10. Thank you very much. Hi, Luis Pedro.
Hi, hello.
We are 10 minutes late, so we will start 11:10 if you don't mind. Okay.
Oh, that's fine. Okay, I'll just I'll mute myself.
Okay, we will start 10 minutes later because Maria's talk was a bit longer than expected.
Okay, Fernando. So I'm typing in chat. It's easier because this is streaming.
Okay, cool.
Hello, shall we start?
Yes, I'm here. I'm ready.
Okay. Hello, everyone. So today we have with us Luis Pedro Coelho. He's the principal investigator of the Big Data Biology Lab at Fudan University in China. He worked previously as a postdoc researcher at the European Molecular Biology Laboratory, and he has a PhD from Carnegie Mellon University and a master's from IST in Lisbon. And he currently works on the analysis of microbial communities in different environments using computational methods, in particular metagenomic analysis and fluorescence microscopic analysis. It's a pleasure to have you here with us, Luis, and he'll give us a talk about Intro to Python. And yeah, the floor is yours. Thanks for coming.
Yeah, thank you. Let me just share my screen. So this will be a fairly interactive talk. If anyone has any questions, just feel free to interrupt and ask questions in the chat. So I'll just start by thank you for the introduction, Zitan. And thank you for the invitation. It's well, unfortunately, I don't get to travel to Lisbon this year, but still, it's nice to see you all. And so I want to introduce Python, and I like to start by talking about the thinking and the history behind it. So there was this other programming language called ABC, back in the day, and ABC was a teaching language. So what this means is that, when students would start college in computer science, they would learn ABC in their first semester, and then afterwards they would learn a real programming language. So afterwards they would learn, at the time Pascal or C or something that could be used, for real programming, so to speak. And the goal of Python was to try to be this best of both worlds, whereby still being a very easy to teach language, but unlike its predecessor, to be usable in the in real life for real usage. And so as a research project, it has been incredibly successful because even though the language has kept growing and kept evolving, it's still fairly easy to teach, as I hope you'll agree at the end of my presentation. But it's also become a language that's used widely throughout the industry, all sorts of applications. It was first heavily used for web development, but in the last especially in the last 10 years, it's become the language of choice for what people nowadays call data science. So it's an open source language, has always been from the start. And there's different ways where you can measure, which are the most widely used languages. You can look at GitHub, you can look at you can look at questions that people ask, etc., etc. But consistently, Python is one of the top 10 languages in the world. So this is what's behind it, so let's start with Python. And so I'm giving this presentation assuming that you know some programming, you've done some, but you don't know anything about Python. And my goal here is to bring you up to date with enough Python to do the practical labs in the summer school. And so if you don't know any programming at all, this will all go over your head probably. And if you're very familiar with Python, please do feel free to just go get yourself a cup of coffee and skip this lecture, because I will really start at the beginning. But I'm going to go through hopefully everything that will give you a basis to then be able to do the tutorials. Okay, so let's start with hello world. So hello world, like this, print hello world. And actually, and I posted the link both in the Zoom chat and also in the Slack channel. So this is a all of this is available, and actually you can run this. So I posted a link to this GitHub page, and if you then click here on Launch Binder, you can then run this live, as I'll show you. So if you click there on the Launch Binder, you will get something that looks like this. This might take a while. So I did this beforehand. It might take yeah, something like 5 to 10 minutes, and then it will open the notebook. So for my presentation, I'm going to present from not from the binder copy, but from the one that's running on my laptop, so that I don't have any issues with with lag or my connection. But you can go to GitHub, get it, run it locally, or click on this launch binder, and you will open. It's a bit slow as a service, but it will eventually open exactly the same as I have on my side. So this is the binder version, and the one I'm going to present is the one that's running on my laptop. Okay, so this is a Jupyter notebook. So I'm going to go a bit over the mechanics a little bit. Okay, I want to go over the mechanics a little bit. So you have these things that are called cells. Okay, and there's two types of cells. There's actually more kinds, but here we have cells that are text. So for example, this one that says Python example, and there are cells that are code. So for example, this one, we can change this back and forth, but cells that are code can be executed, can be run. So I can click here on run, and it will execute the cell and print hello world. Okay, I can also run the cell by going to the menu, so run cells world, or I can, and often I will do this and you might not see it, is I can press Control Enter and it will run the cell. And okay, I can, if I want to add code, I can add cells, sorry, insert cell below. And here I can choose whether I want a code cell or a markdown, so a text cell. So if I want a code cell, okay, and then so we will go through the presentation in Jupyter because it's actually really nice for teaching. It's whether you then want to use it or not, that's fine. I'll get back to that at the very end. So Jupyter is this interface, this notebook interface that's actually not even specific to Python. It started as a Python project, but now people use it in other languages. So actually the name stands for Julia, Python, or R. Okay, so let's look at what Python now looks like. We've gone through the mechanics of the notebook. Let's look at Python. So here's a very simple example. So here we have a list of numbers, and then we iterate over the numbers with a for loop, and we calculate these two values. So we calculate both the total, and we count. So we keep this count n, and at the end we print the total divided by the count. So we print the average value. And there's this quote that Python is basically executable pseudocode. The reason being, even if you have never used Python before, you could probably read this code and have a pretty good idea of what it does and be correct and understand it, and probably even be able to make small changes to it. Okay, so this is the advantage of Python, and So a little bit more just of the mechanics. So here, as we saw before, we've used these variables. We had this total. So we assigned the name total and then we updated it. And it's important to understand that even though you have these separate cells, there's a single context. So that, so if I assign here in this first cell, I assign A equal to 1, and then I print it in the next cell, A is equal to 1. And I can also just type, if I just type the name of a variable, it will just print it out as well. So we can quickly look up a variable value like this. So this is all great, except that it can get very messy very fast if you get out of order. What do I mean by out of order? So here now I'm reassigning A to be 2, and now if I go up and I print A, now A is 2. So in this case, my notebook is out of order because if I read it from top down, A equals 1, print A, it prints 2, but this is because I've executed this other cell not in the order in which appears in the text. So this can actually get fairly confusing if you're not careful. But as always, the right solution to a lot of these problems is to restart everything from scratch. So we can restart the kernel. So if you get confused, you can restart and clear output. So I'll also just point out here that the notebook does help you a little bit in adding these numbers in order. So here the numbers kind of indicate that these things were not executed, one after the other. So they're a bit of an indication that things could go wrong. So here I'm going to restart and clear output. As always, when something goes wrong, shut it down and reboot. In this case, I'm just rebooting what Jupyter calls the kernel, which is, the executor, the Python interpreter that's running behind it. Okay, so that's the mechanics. And so now I'm going to go over the basics of the Python language, and I'm just going to go over this quite quickly. Again, I'm assuming that you're familiar with a lot of this general general programming language concepts. You might just not be aware of how they apply in Python and the exact syntax. So, let's start with types. And you have the basic built-in types that you'd expect. So, numbers, strings, and then also compositive types such as lists and dictionaries, as well a few others. All right, so let's start with integers. Okay, so this works exactly as you'd expect. A equals 1, B equals 2, C equals 3, A plus B times C does exactly as you'd expect, respecting, respecting the priority, multiplication before addition. Nothing's happening here. If floating point numbers, again, exactly as you'd expect. If you specify a number with a dot, then that becomes a floating point number. And again, now things operate in floating point. So, so this also does the basic arithmetic that you'd expect. Maybe less obvious of what happened is that if you mix integers and floats, then what happens is that things get converted to floats. So in this case, A is an integer 2, B is a floating point number, C is a floating point number, and the result is 13.0, which is 13 as a floating point number. So this is maybe slightly different from other programming languages, but when you mix, everything gets converted to a floating point number, and then you have the advantages of that, namely that you can obviously use fractions, as well as a disadvantage that the results are often subject to rounding error. you have all of the basic operations that you'd expect. Plus does addition, minus does subtraction, the star does multiplication. You can do powers, exponentiation, and that's spelled, star star. And if you just add a minus, that does the unary minus, namely flipping the sign. So the minus of 7 is -7. The minus of -7 is +7. Okay. Division is where it gets a little bit tricky because, if I ask you what's 9 divided by 3, I mean, I hope that everyone who's not sleeping would, 9 divided by 3 is 3. The question gets a bit trickier if I ask what's 10 divided by 3, because in fact, there's actually 2 very reasonable answers. So one is this integer division, which is 10 divided by 3 is 3 with a remainder of 1. So this is what my kids learn in primary school right now, is that and if like this, you have 10 cookies and 3 children, each child gets 3 cookies and there's 1 cookie left over. Another actually very reasonable answer is to say that, okay, we do this in floating point, and then we approximate, and the result is 3.333 up to the limit of machine precision. And in Python, both of these are supported. They have slightly different syntax. So the integer division is spelled with this divides, and if we the floating point division, and here I was very explicitly, it's just a single division. So if I just use single division, it does floating point division. And here you can see at the very end, you have this 5, because you are at floating point numbers, you end up with these rounding errors at the end. Okay, so historical note, this was actually one of the changes that happened between Python 2 and Python 3. And Python 2 did not have this integer division and only had the floating point division. But now this used to be a bit of a hassle. It's now solved. So you have the / operation is integer division, like you learn in primary school, or at least in our primary schools here in Luxembourg. I don't know where you are. And the / division is floating point division. Okay. Moving forward, so we have numbers and we have strings. So strings, and I'm going to start with syntax. So here we've seen this. So a name assigns a name, and then we have single quotes, something, 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 single quotes, or double quotes, something, 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 double quotes. And both single quotes and double quotes are exactly the same. Literally the only difference is that if you start with a single quote, you have to end with a single quote. And if you start with a double quote, you have to end with a double quote. And here we've used the plus sign, and the plus sign does addition. So addition with strings does concatenation. So it's John, and then a space, and then a double. So this is what I was saying before. Yes, these are called short strings, and because we'll see long strings in a minute, and we can get special characters by using this / syntax. So /n gives you a new line, /t gives you a tab, and there's a few others, but basically /n and /t are the only ones you ever need in practice. So /t would give you a tab. So for example, here. So we could do something like this. Okay. And if you're paying really careful attention, you might see that the print function, which is a built-in function, is also adding its own new line. So we could do this as well. Okay, so you have So this is very similar to what you're probably used to from other programming languages. And now we have, let's talk about string formatting, which again there's a couple of different variations on this. So we'll start with this format function. Okay, so let's start with syntax here. So here we have a string. So this is just a normal string. So double quotes, then something, something, something. And then we have a dot, and then format, and then parenthesis, and then a single quote, something, 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 single quote. Okay, so you've probably, if you're used to any sort of more modern programming language, you'll recognize this as, so we're calling the format method on the string, and giving it the argument Luis Pedro. So that would be my username. And what this format does is it's going to replace all of the placeholders by its arguments. And so here in this case, there's the placeholder is this curly bracket, and there's one placeholder that's the placeholder 0, and so it gets replaced with the argument. And in the second example, we have two placeholders, 0 and 1, and they get replaced with these two arguments in order. So we'll see this later. So Python starts counting at 0. So the first placeholder is placeholder 0. The second placeholder is placeholder 1. And there's really nothing much more magical than this. You can, and here, we can give it strings, and you can, this doesn't really make sense, but if you give it a number, it gets printed as a number. And you can specify a lot of options, and there's this even sort of mini language about how you exactly do the formatting. I'll leave it to you to look that up if you wish, but just to preempt, yes, you can specify exactly how you want things to be printed out. So as a minor convenience, you can also leave the numbers out and just use curly bracket open, curly bracket close. In practice, you probably want to do something like this much more often. It just conceptually may be easier to understand if you think that you're adding this 0 here to the first one you see, a 1 to the next one, and etc. And so it's just depending on the order in which they appear. Okay, so this is the new style of formatting. There's also an even newer style of formatting, which is actually really, really nice. And this has been available now for several years. So probably I would recommend even that you use this for newer code, although you might still run into a lot of code that uses the old style. And these are called F strings. So this came out just at the end of 2016. And so syntax. So here you have this string, or actually I can show you the code. So here you have a string, right? And it's a normal string. So double quotes, blah, 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 double quotes, except just before the string, there's the letter F. And this is it's the letter F. And F, I'm guessing it stands for formatting. And in the letter F sort of makes this be interpreted specially, so that now these braces, they're still placeholders, but the placeholders are sort of interpreted inline. And so again, if you just look at this, you can probably guess what it does, and it will do exactly that. So, so here it will look up the variable username, and it will replace it there, look up the variable last login, it works for numbers. And you can actually write even more complex expressions inside these brackets, and they work. I think there's a couple of limitations on exactly how complex this can be, but generally it will work. Even as a special variation on this, and this might only be, this is now even newer, is this variation where if you write the variable name and then equals, it will, so this one might not be so intuitive what it will do, so I'll just run it. It will print out the variable name, it will print out, so the variable name and then the variable value. Maybe I'll take this opportunity as well to sort of mention, the current version of Python is 3.9, just came out last year, and there will be a new version coming out in October this year. And if you just look at the dates, so the current schedule is that about a version comes out every year. And as far as I know, this one slide, or this one box 14, is the only difference between anything in the last 5 years or so. So since version 3.6, everything else that I'm showing hasn't changed, but there's a couple of new wrinkles, but we are not covering them here. So this is actually the only example of very new stuff. Okay, so I'm finally going to mention something that you really should never use, but it still works, and you might still see it in old code. And so I'm just going to show it to you just so you see how it works. But there's a lot of good reasons why you shouldn't use it in new code. This is deprecated. But I think is using formatting using this percentage sign, and it's sort of the same principle, but the syntax is different. So instead of using .format, it uses the percentage sign, and instead of these curly braces, it looks for percentage sign. So in this case, percentage sign S, and it will replace. So the percentage sign is where the placeholders are. Really never use this in new code, but if you see it, this is what's happening. It's an old style it's an old style of doing this replacement of strings. Okay, at this point, so we've seen strings, so we've seen how to write them. Let's just give you a couple more things. So I mentioned these were short strings. So there's also long strings, and so here's a long string. So the syntax is that you start with 3 single quotes and you end with 3 single quotes, or you start with 3 double quotes and you end with 3 double quotes. And then you can have, it's called a long string because then you can have multiple lines like this. And so this is an old Kurt Weill song. And if I had used triple quotes or triple double quotes, oops. No, sorry, I have to fight the IDE here, but yeah, so if you started with, so this works exactly the same. So these two are, okay, so that's strings. Okay, we can keep moving on. Let's talk about lists. So numbers and strings, these are simple objects. And now we talk, lists are compositive objects. So let's start with syntax. So here values equals, and now we have this thing, square bracket to square bracket, and then values separated by commas. And then here to access it, we again use this square bracket, and we use an integer ID. And as we kind of saw before, implicitly, in Python, it's a zero-based system, so the first element is always the zero order element. And so this is so this is just as usual. And then the one thing that might not be usual in other languages is that you can access from the end. So if you use -1, that's the last element. So, and -2 is the second to last. So if you use a negative integer, you count from the end. And here, one thing, here we are calling a function len. So this is a built-in function, and len is short for length. So it gives you the number of elements. So here, 1, 2, 3, 4. So I guess this is not surprising. Maybe maybe just as a lark. So what I did, I added if we try to access, so something that doesn't exist. So let's say element 10. You will get an error. So index error, because elements go from 0 up and through, but not including 4. So the last element is element number 3. Okay. So we actually have seen this syntax before in the formatting, where so object.method, and there's a couple of methods. So a very simple one is sorting. We can sort, and so here we have a list of strings. Again, square bracket to square bracket, separated by commas, and sorting sorts alphabetically. We have another important method, which is the append method, which, as the name says, appends an object to the end. So you can also see that, yes, you can change the values of a list. So lists can be changed, and they can grow in size. So here, previously fruits had 3 elements, and now it has 4. Okay, maybe here as an aside, and this is a Jupyter thing. It's not specifically a Python thing, although other development environments will do something similar. Is that if you can get help by adding a question mark at the end of, for example, a method, and a little window will pop up like this. And in this case, this window describes the function sort, the method sort, and you have a little bit of a English language description. So you can see that there's a couple of arguments. So for example, there's this reverse argument. Just so for example, if we sort, it sorts alphabetically, and then we can here we'll see this in a second. So if reverse equals true, then it sorts alphabetically in reverse order. But here the important takeaway is that you can use a question mark sign, and a little bit of this help will pop up, this help window. I'm gonna okay. Okay. All right. So here we saw append before, and so here maybe it's interesting to see that we can. So we have a list of strings, but we can append a number, and we can even have these complex things where a list can contain another list. I mean, technically speaking, a list can contain itself, and all of these things, they work if that's what you want. That's in Python, lists are untyped. Okay, so those were lists. So let's move on to another composite object, which are dictionaries. And so dictionaries are called maps or hash maps or hashes or some variation of that in other languages. So if you and so let's as usual start with, let me try to make the window a bit bigger. Let's as usual start with syntax. So so this goes from this a curly bracket, as we saw before, to a curly bracket. And so we still have commas as separators, except that now the objects, instead of just an object, we have here a key, a colon, and then a value, and then another key, a colon, and a value. And so this maps the name Lewis to this, which is my email, and the name Rita to this, which is not Rita's email. For those who know, Rita is my wife, so this is not her email, but this is actually my real email. And then syntax, we can again use this square bracket syntax like we saw with lists to access elements in the dictionary, except that instead of just using integer indices, we can use the string indices. So this, so this looks up, and we can also use this. We can also use this other very similar syntax. So we can accessing the object with a square brackets and then with a key, and then we can assign, and that will either add a new element or replace an existing element. And we saw LEN, the length function before, works on dictionaries as well and gives you the number of elements. So that's that's what it means. So actually, len is a fairly generic function, and it gives you the size of something. And in the case of a list and dictionary, that's obvious. There's a couple of other types, including types that you can define, where you define what their length means. Okay. There's a type called none. This is spelled N-O-N-E, capital N and lowercase everything else, and it does nothing. It's like a null pointer, but you'll see it show up a couple of times later, because when Python sort of needs to fill in something and doesn't have a value, it uses the value none. Okay, so let's see where we are so far. We've seen the basic types. We've seen the basic built-in composited types. But to be able to really do anything, we need a bit of logic. And so logic is so control structures. And so let's look at the most basic one, which is an if and else statement. So so you've probably seen this code, and you can probably guess exactly what it does. But so again, let's just be pedantic. And so syntax, if if, and then a space, and then something, something, something here, this condition, a colon, and then a block, and then else, so special keywords, colon, and then a block. And this does what you'd expect. So so blocks are defined by indentation. And actually this is like, I think I kind of need to update this slide, because this used to be very much true, that this was a fairly unique feature of Python for widely used programming languages. Again, there's a lot of other languages that use this, but within the languages that are widely used, but I think it's becoming more and more other popular languages are now using this. And the rules are actually quite flexible from the interpreter point of view, but the sort of the unwritten rules is that a block is defined by 4 spaces, and you can, and there's other there's a very precise, you can actually use anything as long as you're consistent, but we are going to use 4 spaces, and the community as a whole, people sort of converge on using 4 spaces. And that's also, for what the editor gives you by default. So if I type here, some sort of, so if I sit, it will give me 4 spaces. Without me having to type anything, just because of the colon, the editor created 4 spaces for me. Yeah, so again, the if a keyword and then some condition, a colon, and then space, you have a bunch of statements, 1 or more with 4 spaces, and then you end the if statement by simply starting to write code aligned with the original position. Okay, this is, and so just the indentation defines the structure. Okay, so we said that some condition, and so we have, before we saw this comparison, does what you'd expect. To do equality, Python uses equals equals. So this again, this is also from a lot of languages use this convention. So because the equal sign is used for assigning names, assigning variables. So to do a comparison to check if A is equal to B, it's the double equals. Not equals, it's exclamation mark equals, then less than, greater equal. And then there's these actually really useful ones, which is A in. So you can check if something is in a list or not in a list. And actually it also works for other types of collections. Okay, so we've seen if else, but sometimes you want to have multiple conditions, and in Python this is spelled elif. Sorry, ELIF. So that's short for else if. So you can have an if, and then you can have multiple elifs, and then you can have an else. And what happens is, as the flow of control goes, it checks each condition in order and executes the first one that's true. So in this case, this is the first one that's true. And if you had, say, great. So if we start, if already the first one is true, then the other ones are not checked. Okay, so I think this is very similar to any other programming language, except that maybe this elif, the exact syntax that's used. All right, so control statements. That's the next one is, so looping. Again, let's start with syntax. For, and then some name, the keyword in, and then a sequence, colon, and then a block. Again, blocks defined by indentation. All right, so let's see the example. Here, students is a list, and then we can iterate over students. And this, so basically the code in this block will get executed 3 times, and each time the name st will refer to one of the elements in order. Okay. We can also loop over dictionaries, in which case maybe less obviously so. The dictionary, sorry, this will iterate over the keys in the dictionary, which we can then use to index the dictionary. Okay, so the while loop, and by now you can probably guess the syntax. And because this is one of the things that makes Python easy to teach, is that the syntax is really very regular. So the syntax of a while loop is the keyword while, then some condition, a colon, and then a block indented by 4 spaces. So here's poor man's division. So we could divide two numbers by subtraction. By subtraction, and the while does exactly what you'd expect. And here I've also introduced the plus equals operation as well as the minus equal operation. And so C minus equals B is a easier way of spelling C minus B. I plus equals 1 is an easier way of spelling I plus 1. And unlike other programming language, there's no there's no shorter way of saying this. So it's I plus equals 1. Okay, just to finish. So in many programming languages, loops are over integers. So as we see in Python, it's more general than that. We can go over the sequences, which is great. But sometimes we really do want to work over integers, and for that there's something called range, which is this special thing which lets itself be iterated over. And so if you go over range 5, you will go over from 0 up and 2, but not including 5. So again, Python starts counting at 0, and then a range 5 includes 5 numbers up and 2, but not including 5. Okay, all right. So I'm sort of speeding up a bit, I guess, as these things, we get used to this. So we've seen these comparisons already, and they do what you'd expect, and they return these Boolean values, true or false. We've actually seen this because I introduced them in the reverse sorting example, and it's true spelled capital T and false spelled capital F. But we can also use the Boolean values directly. So we can just use true, and you can see that if I spell it lowercase, it's not going to work, and you can see it's not going to work because it's not the word does not turn green. All right. So, and many things can be evaluated as conditions. So we can evaluate the list as a condition, and the rule is that an empty list is false. If anything is there, it's true. Same for dictionaries, same for strings. And numbers, 0 is false. Anything else is true. So anything that's not. And this also comes. This can sometimes be a bit error prone, but this is a common convention. Okay, so we've seen these numbers. We've seen these loops, the for loop, and there's these two special keywords: the keyword break and the keyword continue. And so continue goes to the next iteration immediately, and break stops the loop. So this is similar to other programming languages. So for example, here. Very similar to what we had before, where we were computing the average, but in this case, if the values are less than 0, then we continue, meaning that we go immediately to the next one, and so effectively we are skipping over any value that is negative. Okay, so. All right, so functions, again, let's start with syntax. As usual, special keyword def to define a function. Then here you kind of write what you want. So you write your function name, and then parentheses, and then you can add arguments, a colon, and then a block. And then the block is the code of your function. And if you want to return a value, use the keyword return something. And then to call the function, you call it using the function name and then these parentheses we saw this already because we were calling the print function, we were calling the len function, which are built in, but we can also call, functions that we define ourselves. All right. So I kind of skipped over this as this red text, and maybe your intuition was that this is a comment. And that's not wrong, but it's a special type of comment. So it's a special type of comment where it's called a documentation string. So if you write a string immediately at the start of a function, then this becomes part of the function. And then, for example, in Jupyter, we saw this question mark syntax or question mark special function before. We can use it to get this documentation. So if I use this pop-up that we saw before, now it just prints out this exactly what I wrote there. So there's no magic here. So if I change this, so if I change this here, and then later, yeah, so just, and there's actually, and I used this before without commenting on it, is that you can use the hash sign to do a more normal comment. So a hash sign is just a comment that doesn't do anything, whereas this special documentation string serves both as a comment to the people who are reading the code, but then it gets handled in this special way by the IDE, or including Jupyter, etc. Okay, so calling functions. Okay, we've seen this. Can call a function. So here we call it with an integer. We call it with a floating point number. We can have these expressions. So here, so this function takes any type of number actually. So functions don't, the typing, you don't specify the types. As long as the code works, the code works. This is sometimes called duck typing, in the sense, if it quacks like a duck, then it is a duck. So if the code works correctly, then everything's good. All right, so we can have multiple arguments. So again, syntax def, our function greet, first argument with a comma, and then a second argument called greeting, and then here equals, and then here a string. And this means that the second argument has a default value. So I can call the function with either one argument or with two arguments. And we can also call functions. We can also call them with this syntax where we specify exactly what the arguments are. So we specify the, and in this case, the order of the arguments doesn't matter. And this is really, in this case, this is a bit of a tutorial example. It's a one-line function, but when you have a function with 10 parameters because you're fitting some sort of complicated mathematical function, then it's really helpful if you don't have to get the order of the examples exactly right. Okay, and so this is a bit of a breakpoint in the discussion, in the presentation. So I'm going to give everyone a 1 minute break, and take questions here. If you have any questions. Okay, there are no questions.
I actually have one question. What's your opinion on the new typing system, especially applied to machine learning and deep learning?
Yeah, I don't really have a lot of experience. So actually, we started using it in one project in the group, but I don't have enough experience and that was basically because the student sort of started doing it. I don't have enough experience to know if it's helpful over the long term or not. Yeah, so maybe for a bit of background, so there is a optional typing system now in Python. So where you can actually, so here going back, so you can actually say that name is a string, and the syntax is like this. But this is optional. There are some tools that help with this and check. So as I said, I don't personally have a lot of experience using it and to know if it's helpful. I mean, especially in the more like data science projects where your code does not grow to tens of thousands of lines of code. Normally there's a lot of conceptual thinking behind it, but the final result is still quite compact. And so you don't have these problems of trying to integrate hundreds of thousands of lines. So we've started using it internally. I don't have a good answer. Sorry. There was a Q&A. Maybe I can just answer the Q&A. All right, so I'm going to add. Okay. Oh, okay. Yeah. All right. Those are actually good questions. All right. So we had these fruits. Okay. Actually, and so is there an update? Yeah. Okay. Update. So there's no update. There is an extend. So what extend? So we saw append before. So append adds an element. So we saw fruits, and then so if I append, that adds one element, right? And so okay, and if I extend is basically the list version of this, so where I can add multiple elements by giving it a list, or in fact by giving it any sequence. So I ran out of fruits that I know. So here in this case, I'm appending two elements at once. So I append the, so it's the variation where now I've added more than one element at the same time. Okay, so another question from Shagun. I hope I'm pronouncing that name correctly. So enumerate items, iter rows. Yes, okay, so yes, iter rows is only for data frames. Wait, yeah, let me skip this until the end, maybe, if we have time. Otherwise, I'll answer in the chat. Number 2, does format work only inside the print method? The answer is no. That's actually so all of the examples I gave, in fact, only use format inside of the print method. So that's a pretty natural assumption, but it's not. It's technically unrelated. So so if I have so so all the examples I gave looked a bit like this, right? But in fact, I could have taken this and save this to a function. Save this to a variable, and then and then did something else with it. So printing it obviously, but I could also have called another function with it. So for example, sometimes you can, yes, you want to build something and then, so, okay, maybe a slightly less silly example. So we can, okay. So we could do something. So yeah, so we could build up a little string and then use that to call another function with that string and so on. Okay, I might come back to the number 1. Otherwise, I'll answer in the Slack because just in the interest of time. All right. Okay, so up to this point, we had basically Python as a programming language, but now we're going to. So this is a general purpose programming language, and so unlike R or MATLAB, which are, or nowadays Julia, Python has nothing built in for like numeric scientific type of programming or sort of this data science machine learning type of programming. In fact, this was not even really a thing when Python started, back. But there's this one package called NumPy, which is not part of the language built in, but is so commonly used that it's effectively a standard. So it's not a standard in the sense that it's part of the language, but it's maybe what you call maybe a community standard, and so let's actually start with syntax. So we have this keyword import, and in other languages you might have seen keywords like require, include, import, or something like import, and the one thing that's maybe interesting is this as NP, and so this just defines NP as an abbreviation for NumPy, and it's actually really common and to use NP specifically. So not any other type of abbreviation, but NP. So often, even in code examples, you will see NumPy abbreviated as NP. So what NumPy has fundamentally is this array type. So an array is a multi-dimensional array of numbers. So for example, here, A becomes this array. So here I'm calling this basically this array function. I'm skipping over some technicalities, and then here I'm calling it with what you could recognize as a list of lists, and then giving it a bunch of integers to build this A object, and then and then I can access it using the square brackets, except that now instead of a single element, I have 2 indices. So 0, 0, 0 is the first row, first column, 0, 1, first row, second column, 1, 0, second row, first column, right? So yeah, so we have, so kind of a natural question is, I already showed you lists, but those are built in. So, for example, here I have A as this array thing, and then B as a list. What's the difference, and why would I want to use, this extra library with this extra and typing, even if it's not a lot, I have to type a little bit more. Why? And there's basically, I'd say, 3 arguments that we can make. So the first one is just that, it's, so lists have this lists are general purpose, and NumPy arrays are numeric, and so we can have all of this, built-in numeric stuff. So compute the mean, compute the standard deviation, the maximum value, etc., etc. So we have all of these built-in facilities that we could use for lists. We could have functions, but this is all built in with NumPy arrays. So that's kind of nice. But there's going to be 2 other reasons in terms of efficiency and expressiveness. And so for example, so here again, just show you A. We can add an element. Sorry, we can add the value to each of the elements. So A plus 1 adds 1 to each of the elements. So 1 plus 1, 2, 2 plus 1, 3, etc. And the times also works element-wise. I can add arrays element-wise as well. or I can, if I have two arrays, I can add them element-wise. You know, and so, and this is also why I'm calling them arrays and not, you know, and not vectors, because these are, when I work with them, these are not, you know, these are not matrix vector operations. These are just working on each element as its own thing. So this, but if we really do want a matrix vector operation, there's a function called dot that does actually generally more generic sort of tensor dot product, which becomes a matrix vector multiplication or an inner product if you give it. So depending on what you give it, it will do some sort of matrix vector operation, or so generally speaking, it does a tensor operation. So, but that's not the default. The default is that an array works. So if you use the, you know, the plus and the times operation, that's element by element, and you have to use this other dot function to get these, you know, matrix or matrix vector operators. Okay, so this was the argument of convenience, but there's also a very good argument of just efficiency, which is a NumPy's arrays can be really efficient because the, you know, as I mentioned earlier, so a list in Python can, you know, can have multiple data types mixed together. And so this means that, you know, in memory, it kind of looks like, so you have some object that has a little header saying, oh, I'm a list. And then it has the elements. And so, and then the first element has a little header saying, hey, I'm an int, and I have the value 1. And then the second element has a header saying, hey, I'm an int, has the value 2. And the third element has, hey, I'm an int, has the value 3. And whereas a NumPy array looks much more like this. So there's a header, which is actually maybe a more complicated header, that says, hey, I'm an array of ints. But then all of the numbers are just represented, you know, directly in memory in a contiguous blocks of memory. You know, and computers are just really good at handling, you know, numbers in contiguous blocks of memory. I mean, this is, yeah, they're really, really fast. And the other thing is that there's also a lot of libraries written in other codes, in other programming languages, sort of C or Fortran. And so actually, you know, above, when we do matrix multiplication, that's not code that's written in Python, that's code that's written in Fortran that goes back, you know, 50 years. People have spent their entire careers just making sure that this runs as fast as it could. And, you know, maybe just to show you the, another little thing. So for example, here, we're using a magic command called timeIt. So syntax is, so we use this percentage operator, and this means that this is not Python. This is now we're using a command for the Jupyter Notebook. So in particular, this will only work in the Jupyter Notebook. And here we are going to build, compute the sum from 0 up into, but not including 1024. And so here as a standard Python list. And so here we use the list function to convert this sort of weird range object that I talked about at the beginning into a proper list. And here a range gives you the array version of this. And so as you can see, you know, this is faster, you know, but actually not by a lot. And for small, you know, for small things like this, you know, the tens, hundreds, thousands of elements, Python is actually quite fast. But you know, but if you make this a little bit more complex, then the differences start to grow. And so, you know, so for, you know, real scientific data, you know, where you have, you know, or where you're doing more complex operations, you know, now we're not talking about saving a microsecond, not or here or there. You know, now this is a a more than 20-fold difference in speed, and so the efficiency, and this could actually even be done faster with NumPy. And a lot of this comes down to this fact that NumPy arrays are homogeneous. So, unlike the Python arrays or sort of the Python lists that can have multiple types, so all members of the array have the same type. And it's typically either an integer or floating point. And this gets decided when you first create the array. And so if you want to, you can later convert it by creating a copy with a different type. But once you create the array, this is the type. And so here we have this D type, that's the data type. And so, and normally, NumPy will try to guess. And so, but you can also explicitly say what you want. So if you're integers, it gets created as int64, floating point numbers as float64, etc. And so this obviously makes it faster. As I said, computers are really good at this, like contiguous blocks of memory kind of handling. But it's also nice if what you're really handling are data matrices, and and often what we are handling in sort of machine learning, scientific computing, it is sort of these data matrices. It also allows you to express exactly what you want. And you have these, and these are the data types that you can expect. So int 8, int 16, int 32, int 64. So this would be the integer versions, and uint are the unsigned versions. So the version where you only have, you don't have negative numbers. And similarly, floating point, you can decide whether you want 32 bits, 64 bits, or 16 bits. And depending on exactly which computer you're running, you might have 128 bits. And do note, however, that these things, can over and underflow. So here, if you have an unsigned integer, once you subtract. So in principle, you would get a negative result, but what happens is that you wrap around. And so, in some ways, this is a bit the price we pay for the speed, is that now numbers can over and underflow. Okay, so something that actually so a lot of what I'm going to present now fits this thing where maybe it's a bit confusing when you first see it, but actually it's really useful in practice, and this comes up a lot. So let's say we have this array A, two-dimensional array, and actually, I'm sorry. Actually, we saw before that there's this operation A.max that gives you the maximum value, but it's sometimes useful to work along an axis. So we can say A along the axis 0, and so this means that this is going to collapse the first axis, so the 0 axis. And so this is going to give you the max in the first column, the max in the second column, and the max in the third column. Or if you say max, and you can leave out the explicit argument, you can also do it across rows, so the max in the first row, etc., etc. And this works for all of these operations, so min, minimum, etc., etc. And this is really useful. For example, let's say you have a common organization is your rows correspond to instances and the columns correspond to features. And so this would be the mean value of each feature, for example. And so this actually shows up a lot. Okay. All right. So again, let's show this shape is the shape of the array. So 4 by 3. And so we saw before that we could access elements of the array using this square bracket notation. But we can also access individual rows. So this is a two-dimensional array, and if we just access values, this is the first row, which is now an array of size 3. We can access the second row, and if we want to access a column, we have this sort of special syntax where we use this colon, and what this means, the way to read this is kind of a placeholder. So this is the array where a something comma 2, so 0 comma 2, 1 comma 2, 2 comma 2, 3 comma 2, so on. And so if you think about it, that becomes this last column here, which is exactly what we want. So very important is that slices share memory. So the technical term, and you'll see this, is that this is a view. So let's say this is A, and then, so here we get the slice, B, and then we set the value on B, and then we look back at A. This has changed the value inside of A. Okay, so maybe this is a very silly example. So maybe this would not happen by chance, but what could happen by chance is that if you write a function that changes its elements, it changes its arguments, then when we call that function, then it's going to change the original element, so the original argument. So in some ways, if you want to think in these terms, you are passing the values by reference. So here we have A, and again, in this example, you would see it, but if double array was defined, somewhere very far away in the code, it could not be obvious that calling double array with A changes the value of A. So A starts as this, and then so you have to be careful. Again, this is a lot of this is about trade-offs. This means that calling a function is very, very fast, even with very large arrays. Also, if you can have very, very large arrays that barely fit in memory, but you won't have any extra copies. But there's, especially for these smaller examples, you can always just call this copy method and create a copy. So here we create the slice. So here we saw this colon before, and this is a more general version of A 0:10 is A elements from 0 up and 2, but not including 10, and create a copy. And now B is completely independent of A. All right, there. Another one of these, it's maybe it looks weird, but that's actually incredibly useful in practice. Once you get past this initial hurdle of internalizing the syntax, is that we can have comparisons and of arrays, and they work element-wise. So as I said, all the operations tend to work element-wise by default, and this is not an exception. And what's nice is that we can then do. So here we can then take these logical arrays, so these arrays of true and false, and do operations with them. And so when we can do, in this case, a logical operation using the AND operation, and then we can do a numeric operation by taking the mean. And when we take the mean, so the rule is 0 is 0, false is 0, true is 1. And so what this ends up computing is a fraction. So this can be readily interpreted as 25% of the elements are greater than 0 and smaller than 3. So when often you can implicitly convert true and false to to numeric operations, and it works as zeros or ones. And maybe it takes a little bit of getting used to, but there's a lot of uses. And so, for example, another use is that so we can use these logical arrays as indices. So for example, and these two pieces of code do exactly the same thing. So we can index the positions of A where A is less than 0 and set them to 0. Or in this case here below, we are multiplying A by a condition. And so this multiplies by 1 in the cases where the condition is true, and by 0 in the cases where the condition is false. And again, this is maybe takes a little bit of getting used to, but you can express a lot of often useful operations like this. Okay, so I'm going a little bit over time, but since we started late, I think I'll finish in the 90 minutes. Okay, so some very basic helper functions. So zeros builds up an array with zeros, and you can give it the size you want. Maybe not so obvious that the double parenthesis, and this is because the first argument is the size, and so we saw this before. This works actually, but Python has this other variation called the tuple, which looks almost exactly like a list, except it uses the parentheses, and unlike lists, it can never be changed. So it's some sort of immutable list. So zeros, there's something called ones, builds up an array of ones, and there's something called zeros likes, as well as a variation called ones likes that takes an array and gives you another array that looks like the first one in terms of its shape and the data types it contains, but it's filled with zeros. Okay, so one last thing I want to show you or almost last thing I want to show you is this matplotlib, which let's actually see, which is a library for basically plotting. And so there's a couple of different ones in Python actually. So unlike and there's people who use other things other than matplotlib, but matplotlib is perhaps the biggest player and the most widely used. Again, it's not built in, and so here, so we have to import it. And so here I'm also setting the style so that the plot looks like I want it. And then here x, another special helper function linspace. So this means I want x to go from -4 to +4 and have 1,000 elements equally spaced. There's also a variation called log space, which would give me the 1,000 elements, in logarithmic spacing. And then I plot x against x squared times the cosine of x squared. So again, you have the cosine, the sine, sort of all the exponential. These basic functions, you should expect them to be there. And the plot looks like this. So this used to be a bigger problem, but sometimes depending on how you've set things, you might not see the plot. And this magic command matplotlib inline says that you want to see the plots inline and not in a separate window. Okay. Let's see. Okay. Yeah. I don't often use notebooks, but this one I sometimes really like, which is this interactive exploration. and this is a bit of magic actually. So I'm not gonna, I cannot explain all of the magic, but so if you import, you can import these widgets, and there's a lot of flexibility here, but what's actually nice is that a lot of the built-in stuff just kind of works, where you can then, you can define your function, or you can define a function to do whatever you want, and to say you want to interact using this sort of @ interact, and then power equals, and here I say it goes from 1 to 10, and it draws this little thing, you know, and I can just play around with it, and every time I run it, it's going to call, every time I change, it's going to call the function, and it's going to do something. In this case, it draws a different picture. I mean, so this doesn't, you know, this doesn't work if the function takes an hour to run, but if it takes a few seconds, you can quickly play with a couple of variations on something and explore interactive. You know, and what's cool is that you can get these sort of really trivial interfaces with 95% of the time, as I write here. You know, if you can just do, you know, you get enough, you know, so this, we saw this before. You can also, if you give it a dictionary, it's going to build this sort of drop-down menu, and if you give it a Boolean, it's going to give you a checkbox. You know, and you know, and oops, okay, and I guess I messed up here something. Yeah, and then you can, yeah, you can do, yeah, your function can technically do whatever it wants. Yeah, so okay, final words. Maybe I'll post this on the Slack channel as well. So I just finished saying, you know, this is actually one thing I like about notebooks, but you know, and I enjoy notebooks for presenting and for tutorials, because I think it also allows the audience to follow along. But for day-to-day work, I rarely use them. And you know, I also post this, you know, this well-known "I don't like notebooks" talk. So you know, so if you don't like it, don't use it. I mean, you can, you can use, you know, traditional text editors, you know, Vim or Emacs or Nano. You can use an IDE like Spider, which I'll also post, or you can use the shell. There's a variation of called IPython that works in the shell. So everything I talked about, except when I said, okay, this is a Jupyter thing, everything else is about Python, and so you can use the language, you know, anywhere you want. So this, maybe I'll just show Jupyter real quick. Yeah, so if you want to, so finally, if you want to learn more, so both NumPy and the Matplotlib, they have a lot of documentation. Yeah, so I'll post it. You know, the links are posted in the notebook as well, so everything is there. So I'm almost out of time. Let's see if there's any questions in the Q&A. And maybe I can go back to Shagun's question about the enumerate. All right, so enumerate is, yeah, so enumerate is a way to go over where, so okay, let me go. So we saw this before, where we can iterate over a list. Okay. And we also saw that we can iterate over a range. And enumerate is a way of iterating over both the list and the range at the same time. And so instead of just one thing, I didn't show this, but we can go I, F. So now we want two things, and enumerate I will become the index and F will be the value. Okay, and I can go over a bit more detail later, but this is what it does. Did someone raise their hand? I don't know if you can unmute yourself, or how does this work?
You have a Q&A chat session if you want to place any of your questions.
Okay, maybe I'll just show the one, because we're also running out of time. So, all right, so I talked about, and just, maybe just for those, so we have this dictionary, and I said we can iterate over the dictionary, and it iterates over the keys, and that's true. But if we can also iterate over, we can ask to iterate over the items, and an item is basically a pair key value. So now we don't have so key and value, and so items allows you to iterate not through both the keys and the values at the same time. So it's just okay, and I think we're also out of time. So I mean,
Yeah. So I don't know if there are any more questions or.
So there's one question from Elio, and actually this one is. So this one is. Does the behavior of changing the content of an argument from within the function execution apply to all Python data types? Okay, this is a little bit more yes and no. In general, all of the compositive types, so lists and dictionaries, yes. But then the basic types like numbers and strings, so technically you cannot modify them. So technically there's no way to modify a number. So okay, let me maybe give you an example. So when we do this, there's an object A, and we are modifying it by appending it with a value. But with a string, or let's say n equals. So here, there's an object 0, and then we are reassigning the name n to a different object. That's the object n plus 3. And so we haven't changed the original object. And this is all just a short notation. Right. So because, for example, let's do it this way. So in the first case, B and A are just different names for the same object. So when we modify this object, either by using either name, we are modifying the underlying object, whereas numbers, whereas numbers, you never actually modify the underlying object. You can just reassign the name to a new object. There's no, you can kind of tell that like there's no methods whereby you can change, like there's no, you have to use this equals, and even this plus equals, it's just a shorthand for this. There's no method in which you can modify the actual object. Whereas with a list, you can, append really does modify the underlying object. And the same for strings. So you can build up new strings, but you can never, and strings have some methods, but none of them actually modify the actual content of the string. They might give you information about it, but you can never actually change the object itself. So the answer is that yes, all applies to applies to all Python data types, but in fact, many Python data types are immutable, and you never actually change them. And finally, and maybe I'll answer this last one, Camilo Thorne's question. The answer is yes, you can apply to any arbitrary string with placeholders.
Okay, so if there are no more questions, thank you again, Luis, for coming and for giving the lecture. And we'll resume after lunch in the afternoon.
Thanks everyone.
Thank you, Luis. See you next time.